We gotta find something to listen to. There we go. Alright. You guys should be able to hear me. You should be able to see me. Alright, what are we working on today? We're not working too hard. We're just kind of hanging out and doing some Linux. And probably background it with some networking stuff. People have been asking me about some networking. So where I have time, I've been trying to fit in some networking stuff. Also, I need to show you guys around the updates to the home lab that we've been putting there. So I probably want to show that a little bit for, you know, the hammer block stuff. Some of you guys might have missed that. In the home lab, we have quite a bit more systems now than we did even the other day. We have now all of the Rocky servers and then all of the hammer block servers as well. So we're building that part of the range out and the stuff that we're messing with for the security group. We're getting a security administrators group going soon. So people that want to focus on, you know, Linux, we've already got the Linux systems admin course. And then some of you guys want to get more involved with the security side of it, although, you know, I think it all kind of melds together. But the security focused group is going to be coming up as well too. So for people that don't know, we got quite a bit of stuff going on in the Discord in general. So let me pull this up for you guys. If you guys haven't seen our Discord, we got some guys working in, that's about 4 hours from now, but it shows it in your time zone. So if you do stuff in there, it'll be in your time zone. And then the Linux sysadmin course is starting up in March again. So that's a 16-week course. That's a pretty significant time commitment for some of you guys, but let me get out of there. That's a pretty significant time commitment, but I think there's some value to it. There's a lot of stuff that you can kind of learn about how Linux interacts with an organization, how a company might, you know, what they're going to call on you to do, what the work's going to look like, how you're going to be more prepared to be a sysadmin. And then the reason I focus on sysadmin is because for you guys that want to get into doing this professionally, sysadmin is where you start a lot of the times. You may go over into engineering directly, but almost universally that's going to require some college and some other stuff like that. So I just would say, you know, learn your sysadmin stuff, get in, move up, you know, that kind of stuff, right? All right, so since we're hanging out here doing this stuff, we've got the Linux stuff going. I showed you guys kind of the added servers. We have 25 new servers actually in the hammer block range that people can access if they want to through the Linux course. And I was just going to go today over the primer a little bit for networking, talk about some networking. Some of you guys had asked about this. I do need to add the section to VLANs in it still as well, but I've been super swamped with work. I haven't even streamed in like 4 days, so this is my first time being on for a while. So we'll do some networking, talk shop. I would probably say what I'm going to show you guys here for people that are interested. This is probably analog to maybe a lot of this would be kind of similar to like what you might be studying for like a Network Plus if you were going to go for a Network Plus type cert. I never got a Network Plus cert. I had a CCNA, so like early on in my career, the CCNA kind of superseded anything you needed from Network Plus. Plus, it was very specific to the type of networking that I was doing, so it made sense. But I think it's still good. There's a lot of value here. And I think a few people in our group were actually getting ready for their CCNA as well. So there's that. I've been adding as we go. I've been going in Discord. I've been adding these little discussions because some of the guys asked me to go. I had said, hey, you know, I'll put together little discussions if you guys want to go through and work through, you know, Wireshark and different tools and learning some of the networking stuff. So I've been showing that. And then I highly recommend for people who don't like networking, there's a fair amount of you that are like, Scott, I don't want to pick up a single bit of networking. I just need enough to be a Linux engineer. You're like, I need just enough to get into this field, but I don't want to be an expert in it. I'm actually okay with that. Not everybody loves networking. So this is the book that I tell you guys to go spend some time with. because it's one, it's free. Free's one of the best prices around, and two, it's really good. I want to say it's like the first 170 pages or so that give you all the primer I think you need to at least do some networking and do some system stuff. So, all right. But anyways, this is our Prolog networking primer. There's a whole video on this one. So if you want to go see this in kind of like its raw form, that's there. All right. So quotes get you interested. These come from XKCD. I linked them there. But, you know, the types of computer problems, you know, if you have normal problems, you're over on the left, and you start to get networking problems, and networking problems can just baffle people and really cause problems because you've got different types of issues that occur. There's repeatable issues. Repeatable issues are probably my favorite to troubleshoot because they're pretty easy. Like, I could repeat the problem, I could see the problem, I can see if it's going to logs or not, and then I can fix it. The types of problems that happen in networks a lot, which they mention about believing in ghosts, is transient problems. Problems that only occur from like 8:25 to 8:27 a.m. in the morning, and you're like, why the heck does that happen? And then you find out it's because somebody was standing on the cable at that time every morning. So, you know, you just find weird stuff in networks, right? So network problems tend to be different than other types of problems that we get in computing. Hey, Shania, how's it going? Yeah, I just took a little bit of a break. I've been working a lot, so I just haven't been streaming as much. And then they talk about pushing buttons and stuff. All right, so here's the topics. We'll talk about the simple communication model. I've been showing this to engineers the entire time I've been teaching college. It was shown to me, and it always resonated with me because it's, at the end of the day, we want to move data from here to here. We want it to be effective in its type of communication and its reception. We don't just launch data off into the night. We want data to be captured, and then we want to make sure that that data isn't affected by entropy and time and all these other things, attenuation as signals weaken and go the different places. And then I don't heavily go into that, but that is more of like a physical layer topic where, you know, all signals degrade over time. No signals ever do anything but degrade in our observations, right? So we have to make sure the signals are getting there, the signal to noise ratio is high enough so that the signal can be understood, and then the signal can be passed up through the different layers. So that's what this is going to be about, this networking type thing. Where I can, I'll tie it back to systems, you know, Linux, because that's what we really care about is Linux. But networking is important, right? And then major kind of high points here about things that I think that you kind of need to know. I don't dig into this like I do with college students because they are, you know, they're doing an engineering background. I will dig into this more if you guys want, but I try to show you just the basics. I think of this a lot as just the basics to go past like a Network Plus or CCNA. That's what I think is kind of the minimum that you guys need. All right, so the terminal course objectives, these are the things that if you were to sit here and listen to me, and if you were to do some of this with me, I think that this is what you could do. You could describe the components of computer networking, like what are the pieces. You would understand how and why we subnet larger networks into smaller ones. I think that's big. And then understand the flow of data through the network, which is this idea of protocol data units or protocol data units, however you want to say that. And how they flow down through the different layers of the OSI model, right? And then I want you to understand the term modularity because that's an engineering term that's heavily important in pretty much all the things that we do. Shadow Developer, what's the book about? Yeah, the book's about Linux. Yep, Shadow. Yep. I'm not talking about the book right now, but that is about Linux. Yep. Out of Scope, Becoming an Expert. Like, this is a survey of high-level concepts. You should have enough to dig in and go learn about other things that interest you. It's the same thing with that book on the IBM Red Book that I linked to you guys. That's a free book out there. That book is about networking. Maybe that's what you were talking about. I'm not sure. Over on Twitch, hey guys, how's it going? I'm just starting out, kind of getting back into the swing of talking, I guess, because I haven't been doing a whole lot of streaming the last few days. So, all right, so these are our terminal course objectives. Here's the simple communication model. I picked this up early on in my engineering career, and I think the way it was presented to me was kind of like a challenge, and it's the way that I challenge other people. You will never find a simpler model of communication than this that works. This is the simplest communication model there is. In fact, you will not find anything in which communication is occurring where these 5 components do not exist. What do I mean by that? I mean, if you're looking down at ants that are talking with chemicals, if you're looking at rockets and satellite communication, the furthest distance you can think of, these 5 components will be there or communication will not be occurring. And you say, well, what about this? Nope. All 5 of these components must be there. That's just how it works. All right. You have a sender, a receiver, a message, a medium, and noise. So the sender is going to encode, right? There's an encoding of information via what we call a protocol. Protocol is the rules that govern communication. The rules or steps that govern how communication occurs. That's all a protocol is. The protocol right now in here is I'm speaking English, right? I'm speaking it at a normal conversational cadence. I am speaking at a normal, what we would say probably like a 40 to 60 decibel, range of sound, and I am, not, I don't know, there's probably all kinds of other things that are happening. I have some music in the background, so that's going, but a sender is encoding information and sending it across a medium where it's affected by noise in some way, and then it is received by a receiver on the other side that's going to decode the packet. If I encode on my side, you have to decode on your side. If I encrypt on my side, you have to decrypt on your side. If I compress on my side, you have to decompress on your side, right? And throughout those 4 individual components, there's always noise affecting the signal, right? That always happens. What about quantum entanglement? No noise. I would like to see a system where there's no noise, but I think that's even if quantum entanglement does, people say, oh, there's not, there is still going to be, as you go to read the signal, there's always going to be some type of friction. There's always going to be something. Yeah, everything's going to be subjected to some type of noise. In fact, we talk about this a lot when I don't get into it in this talk because this is lower level physical layer stuff, but if you go and do like some ham radio and do for people that want to get into signals, the interesting thing about signal work, right? And this is my background. My degree is in network communication management, so I did a lot of signal work. You've got a actually, do I have a blank screen? I don't have a blank one to draw this on. I'll just draw it real quick. Hold on, let me get my little pen out here. Let me show you guys something here real quick. I will use blue. All right. Where I want to go with this is let's say we're starting to get into, we're not really doing signal talk right now, but let's say that we are, over a course of time, we've got a signal, which is an oscillating sine wave of some type, right? And it's not pretty, but this is maybe over here 1 second. And then this, the oscillation of the wave down and back to here again, if that happens twice, would be like a 1 Hz, because a hertz is every oscillation of the wave within a second, right? So this might be like 1.5 hertz or something, if it was really that, right? Anyways, where I'm going with this is, as we start to compress more and more hertz, like you guys have heard of like megahertz and all these things, and gigahertz, right? So GHz. And gigahertz is just the idea that I put more of these in here. So maybe I grab a different color real quick, and then I have this other signal wave that's going like this, right? And most of you could look at that and go, well, there's more hertz, there's more energy in that wave, right, as it travels. Well, the waves that we're dealing with are they're electromagnetic waves. So there's an electric component and a magnetic component to them as they traverse through like air. And where I'm going with that is, as you compress more and more down, first of all, real quick, between this distance of 1 second, which of these lines travels further? This is an important concept. This one here is traveling less than a higher frequency. So a higher frequency does what we call attenuate faster. It actually loses strength and becomes weaker in the environment because it's traveling a longer distance in the same amount of time. Similar to that, though, is as we press more and more energy into a cable, for sure this happens with cables, the electro part of that wave that's traveling is going to cause friction across copper. And friction always causes heat, right? It's always a transfer of heat with friction. So technically, as you push more and more hertz into a cable, you could cause that cable to, reach some kind of point where it's going to start on fire. This actually came up if you ever go study like the Telecommunications Act of 1996, where we had to limit the amount of hertz you would put through a cable because people had old phone lines. So like back in the day, we used to use modems on phone lines. And if you put too much energy into that phone line, you would burn people's houses down. This was a thing that kind of this was a big problem in the 90s. I wasn't in networking at the time. I was still just a teenager, but I do remember that we could only go so fast on our modems. And then I learned later when I got out of the Army and went in college that that's part of the reason, was because as you push more energy into the same thing, exact same things happening right now with system chips. They have been able to get the switches very small on CPUs. But as you push more and more energy across that chip, there's a thermal component there that you just can't dissipate heat fast enough before those systems are going to have problems. And that's why they've been looking for, as was mentioned earlier, like the quantum, the smaller. At the end of the day, they're trying to get smaller and more switching decisions to happen across the CPU at any given time. And there's a component of that where the more energy you put in the system, the more you're going to have. There's always all electrical systems have EMI either being affecting them as they're operating or they're generating it. So as you push electrical components closer to each other, there's a bleed over. This is why like RJ45 cables are twisted, because the four cables that are the four cable pairs that go down an unshielded twisted pair cable, they are twisted actually at different lengths. If you were to take a 100-meter cable and unravel it all, you would find that they're different lengths of the cables because of the twists. But that actually causes the EMI, the electromagnetic interference, not to jump to the other cables as much. It's always there, guys. There's always noise in the system. You can't remove the noise. It's not possible. We can muffle the noise, but this model starts to go into all the other things we do in signal. So like the sender over here, I'm putting a certain amount of strength into a signal and a message that I send, and in here this noise is affecting it as again, signal to noise ratio is one of the most important things. When it gets to this far side, is the signal strength enough for me to capture out what I'm reading? That is affected by whether it's a digital or an analog signal, right? That's also important. If it's a digital signal, we can clean it up, and as long as we keep cleaning it up, we're always stripping the noise out. An analog signal, we amplify the noise with the original sound, and there's a bunch of stuff there. But we're not getting into that too much. We're just doing simple communication right now, right? The twistiness part of each category. Fair, yeah. So these are, again, this is just a primer course, so I do dig into some of that stuff, especially with my college students. But if any of you guys you ever catch me on Discord or something, you want to talk about that stuff, I have presentations I can show you guys on that kind of stuff and digging into that. This is some basic terminology. You're going to see TX, you're going to see RX. That's going to be a big thing in your career. As an engineer, TX will always mean sender. RX will always mean receiver. So transmission side and receiver side of a cable communication, right? And if we're down here, if we're looking at this, right? So we pull up our actual system here. This is my home lab here for people that haven't been around. Let's go to like Rocky 1, and I just go like SAR-N, and maybe I say TCP and ETCP. ETCP, yeah, 1. We'll just go 1. And now this will keep track of system information. I can also do, this one doesn't show it as much as I think Dev will. Dev will show this a little better, I think. Yeah, so you'll see the received packets and the transmitted packets. The receive kilobits per and by the way, when they do capital B, they mean bytes, right? So that's bytes per second. So this is more when I look at this kind of stuff, and I always explain this to network engineers. We're not trying to be network engineers, guys. We're trying to be Linux engineers and systems engineers that just happen to know some networking. That's what the primer's for. But operating system people, systems people, server people tend to look at stuff as like, how many bytes am I getting? But network engineers always, almost always, are dealing with the number of bits as throughput. So always, like you might never have thought about it before, but a capital B means bytes, and a lowercase b means bits always, right? And that's kind of a standard that you should run into everywhere. Guys, I'm missing a lot of chat. I'm sorry. With the gradation. Yeah, guys, this is all networking stuff, right? Yeah, Moop Moop, thanks for being here. Hack the Planet, thanks for being here. Functional difference between Red Hat Enterprise and Rock. Hack the Planet, there's not, except for when you get into like updates and support for the most part. When did we really start using KB? Yeah. So there's kibibytes as opposed to kilobytes. So there are differences between those, and there's some stuff you can calculate between them. And MB instead of megabytes. In fact, the place you'll find that conversion most often, that I think anyways, is for people that start doing Kubernetes. You're gonna find that, and it's 1,000 versus 1024, and then the difference just keeps getting further and further along as you start to break those down. Yeah. Curse you. Yeah. Well, we used to call it, the one was the sales term. The sales guys would give the actual numbers, and then we would get the actual numbers after, right? And we could show that. There's a bunch of stuff in our system that can show that. But real quick, data circuit equipment and data terminal equipment, these are things that you're going to see on RFPs and wiring diagrams and stuff like that. But the data circuit equipment tends to be the ISP side of the connection, and if you're using any type of serial line, they're going to be responsible for the clock rate, right? And then data terminal equipment is typically your side of the connection to the WAN, and also these things function as a component of the demarcation point. Demarcation is always the point at which one autonomous system ends and the other one starts. An autonomous system is like what I own and what's under my control as a network or Linux systems engineer. That's my autonomous systems. Everything that I control that are mine. The place where I touch another system like that is the demarcation point. Now, demarcation points are physical if we're talking like what I'm renting from an ISP. Yeah, it's the end of their responsibility, and it's the start of ours. If you guys have ever called like a Cox or a CenturyLink, communications, and they go, hey, you know what, I'm not seeing your device, go ahead and reset it or something. You reset the physical modem, and then they're like, I'm seeing the MAC, and then they just hang up on you. That's kind of what it's like. Like, if they can see to there, they don't deal with any of what happens to those frames and delivered traffic after it gets there, right? That's what they don't care about. So demarcation is the end of one person's responsibility and the start of another. And then a metric is any unit of measurement we use to differentiate systems. The reason metrics are so important in systems world and engineering in general is this. This is why metrics are so important. If we come back over here and you're looking down here at this and you're saying, hey, I'm getting pretty good receive and transmits, the line is good. You see no error. You see, the amount of traffic you expect right here, let's say. But I'm up here looking at like retransmits and shortened packets and things that are failing. And I say, no, this is a bad link because compared to other links, it's functioning at like 10% more errors than normal. And you go, no, but I'm getting the throughput that I expect. And I say, yeah, but no, you're getting a lot of errors, and we're talking past each other. We're using different metrics of how we look at the problem. Now, this is why it might matter, is maybe you, as maybe you're a developer on my systems, and you're looking at it and going, yeah, my stuff's functioning as I want. And I say, yeah, under low load, your stuff's going to be fine. But when we ramp you up to production and you go to 10 times or 100 times the throughput, the errors that we're experiencing won't hold, if that makes sense. It's kind of like I tell people all the time, you patch a bike tire. If you've ever patched a bike tire, you fill it up with air, you put it down underwater. Sometimes you put soap on it. You put it underwater, and you see where the bubbles come out, right? This is how you patch a tire. Like if you ever were a kid and, like me, I used to have to go everywhere on my bike, right? So I check, find the hole, patch it, right? Scrape it, put your rubber cement, put your little patch kit on it, whatever your patching process was, right? And then you let that dry, and then you go put it back underwater, and there's 3 other little ones that weren't bubbling before, but now that one's fixed, that pressure starts to come out. And that's kind of how like systems works. We find the thing that's the problem now, and then it causes pressure points in other places, because now, anyways, my point in saying that is when the system looks like it's good here, but I'm looking at something else, there can be problems. Anyway, I'm just giving an example, but the point is to understand that we have to be looking at the same things. We have to be talking about the same metrics, or we're doing what's called talking past each other, or ineffective communication, whatever other things you want to talk. Frame relay circuit had acceptable error frames according to what I thought. Provided school made good, they were looking for yeah, and this is true of like maybe systems work, like I'm not a software engineer, but I've worked with enough of them to know that like maybe a race condition in testing only happens once every 1,000 times, and for somebody that's just sitting there not thinking about the big picture, that might be fine until they realize no, when this goes live in production code, any one project, any one job, like maybe you're running some big project job, is going to call that function or tool or whatever you have millions of times. So now what you thought was an acceptable, it's only like 1 in 1,000 in testing, that's a really low. Yeah, but we're literally doing it millions of times a second. So now you're talking about hundreds of errors a second through your bullshit. You got to get it reduced to 0, right? It's the same thing with memory links and all that kind of stuff. Went out to O'Reilly and found that there are a lot of mechanisms meant to prevent errors. A lot of mechanisms. Yeah. Oh yeah. There's a lot. Actually, I sometimes get down into, so not in this talk, but in other talks, I talk about when we actually pass 1s and 0s across a line, and we start to talk about the signaling. So there's different ways that we can signal an actual 1 or a 0 across a line, and it may surprise you guys to know, or you may look at it and go, well, Scott, actually, no, it's exactly right. The sender is using an encoding scheme, so on this side it has to be the exact same decoding scheme, right? And like a Manchester encoding scheme is either a positive or a negative 3 voltage on a line, or 5 voltage, whatever. I think it's 3 normally. But the point is, then it's the transition between upper and lower that matter. And the reason I bring that up is to say that I don't remember exactly where I was going with that, but the point is we have to be talking about things the same way. You can't be using Manchester on one side, which is a non-return to 0 NRZ style of passing traffic, and expect something else on the other side. And there's reasons that we use NRZ style, which is non-return to 0 style, and it's because now the systems are they're constantly aware of each other, if you want to think of it like that as well. Wow, nice. Almost forgot about SAR. Yeah, SAR is a great tool. I use SAR for a lot of stuff. There's one pitfall you might fall into with SAR. If you ever can just run SAR like this, I want to show you guys this. This was just somebody mentioned on YouTube SAR. SAR does 2 things really well. It's SAR and SAR-R, which will give you the CPU or the memory of the system. I think there's also maybe like a D. Yeah, and this will show you the disk, right? But if you run SAR in the system, it only does things. So I want to show you guys something real quick here. It only does things at 10-minute intervals, right? So here's all the devices, and then 10 minutes later, all the devices. So you might look at this and see averages and think, devices look good, memory looked good, the processing looked good. But I want to tell you that this is actually kind of a trap, kind of a pitfall in systems world, in the Linux world. Because if these averages, let's say these were a little higher, and maybe we sat at like a 70% idle, so like a 30% usage, like with a web server or something. And then you come in the morning and you see, you're over here and this is like 30, 30, 30, 30. You're getting 30% all the way down. And then you have like a 31 and you go, whatever. And then you 30, 30, 30, 30. So you think, okay, good. But these are 10-minute averages, guys. That 131 that showed up, I'm just making it up, but that 31%, that could have been a 1-minute spike at 100%. and then just over the average, it only raised the average by 1%. This does not deal with acute problems. This deals with like the day in the life of the system, if that kind of makes sense. This will not help you go and troubleshoot acute problems that happened at a very specific time. You need other tools that are better at that kind of stuff, which would be more like, there's Ranger. This is an acute check on Ranger. You would want things more like this, where I can dig in to exactly that CPU range and see exactly what was happening at exactly some time, right? Like right here, I could see exactly at that time, here's what was happening with my CPU, and then it dropped off at, 440 and 38 seconds or something off the system. And I can dig in exactly to when something happened, and I can see that it was spiking at nearly 100%, and then it dropped. So there's different tools that are going to give you guys different things. This is another important thing about metrics is they're units of measurement. They should be standardized as units of measurement. Like I shouldn't be talking kilobytes and you talking kibibytes, and I shouldn't be talking like in the weight room. I shouldn't be talking pounds and you shouldn't be talking kilograms, because they're different measures. You got to be talking and standardizing your measures so that things meet. Otherwise, people are just gonna. Raleigh read. That's actually really funny. I read a thing. He said, we lose money on a transaction when we make it up in volume. Yeah, I read a thing about a guy who asked his buddy was selling shirts, and he goes, well, it takes us $17 to make a shirt, but we sell them for $16. And he tells them, we're losing money. Yeah, we're losing money on each transaction, but we make it up with volume. And you're sitting there going, no, that's not how it works. That's not how any of this works. Yeah. And Middle Geek, that's exactly right. You have the instantaneous rate versus the average, because again, like looking at an average over the last day, I might look down and go, there's no problems. But if there was a spike, even for a minute, that could have caused tremendous outages for people. That could have caused a reset of all cache data. That could have done all kinds of things in the system. And this is why we need to be able to narrow things down by time and all this other stuff, which is different talks, but metrics for now, unit of measurement. All right, so there's three primary types of addresses you're going to use a lot as a Linux engineer. There's going to be your layer 7 DNS type addressing. Most of us think of this as like just human readable, right? Google, if you went to Google right now and said ping Google, or you did host or NSLOOKUP or dig, those four commands would all resolve to an IP address. And then your computer would communicate over that IP address. Well, the thing is, it's way easier for me to remember www.google.com than it is for me to remember 172.217.12.132. Even supposing I could remember those four numbers, those four individual octets, it changes. So why don't I just go look it up when I need it, right? And that's kind of how the DNS works. There's also IP addressing, which we're going to heavily go into here in a second. So IP addressing is either IPv4 or IPv6 style addresses. And sometimes you'll find that in your systems that those are dual honed, so they're actually pointing to both. And then there's MAC addressing. MAC addressing are the physical addresses that exist for your system, right? Couple things to note. As you come down, DNS addressing is always in the format where you've got the top level domain, right? Top level domain .com, .org, .whatever over here. And then you have your domain. And then if you have any subdomains off of it, they would typically be to the left with a dot before it. IP addressing is IPv4, which is the 32-bit address that we express in what we call dotted decimal notation. But behind this is what we call, there's an octet for each one of these. So 4 bits, 4 bits, 4 bits, and 8 bits. God damn. 8 bits, 8 bits, 8 bits, and 8 bits. I don't know what the hell's wrong with me. Totaling to 32 bits, right? And each one of those can represent the numbers between 0 and 255, because that's how many states of nature those bits take. We're going to get into that heavily here in a second. But Some of you are going to be like, God, I can't even believe this guy's talking about this. But I'm going to give you guys my little subnetting primer that I give college students that I need to record one of these days and just put it on YouTube because people are always asking me to show it. But IP addressing works like that. And then MAC addresses are 48 bits long, expressed in hexadecimal. So each one of these hexadecimal bits represents hexadecimal characters represents 4 bits underneath. So this is 48 bits long. The first 6 of the hexadecimal, representing the first 24 actual bits, are the hardware or the device manufacturer, and then over here is the physical device. What we call like the individual it's the individual node or product information. MAC addresses only need to be locally unique. They do not need to be globally unique around the world. However, IP addresses do need, if they're being routed on the internet, they do need to be globally unique addresses. So there's only one for any one endpoint station. Internally, we have non-routable ranges, which is part of the ARIN number registry, right, where there's internal range numbers that can never be routed, and we can all have those. You can have the 10 range, which is 10.0.0.0. There's the 172.16 range that you can use, and I believe that 172.16 range also goes up to 31. You could use all of those internally, and then the 192.168 range with all of the individual components that are inside of there as well. Yeah, that's yours and nobody else can have it. Yeah, and these are the easiest to spoof, but these ones also don't, as we get into kind of the communication between them and how they interact, these become analogous to kind of like your name, and these become much more analogous to like the street you live on, if you want to think of it like that. Because these are going to change where you are physically and logically in a system, and these are not going to change where you are physically or logically in a system. Similar to if you picked me up and put me in a different room of my house, my name would still be Scott. But if you picked me up and put me in a different room of my house, and then you wanted to hit me with like a one of those orbital lances, you would have to use a different address, from a global positioning standpoint, to hit me with that lance or that laser, right? Anybody here know it? You've seen those little orbital lances? I think they've been putting them in video games and stuff more, but they've been stories and stuff like that. I pick you up in a brothel. Yeah, I'd be in trouble. I'd probably be divorced. Well, actually, no. I don't think the wife will ever divorce me. She'd probably kill me, but I don't think she'd divorce me. All right, I have to say in game, right? That's the way that people get away saying that kind of shit. All right, anyways. So let's do a quick binary rundown. Let's pull out our little pen here. I got my little stylus pen. Only because I wanted to be better at drawing, so I bought this little stylus. Also, the thing was only $30, so it was like the best little purchase, this little Wacom tablet or whatever. I found out that Wacom sends all my data over to China, but it's like, whatever. They can have my data along with everybody else. All right, I'm just kidding. Just kidding. Yeah. Let's start with, I always ask this, but I'm just going to start because we're doing the real networking talk here. Let's start with something that most of you probably did in like 5th or 6th grade. And let's throw a little dollar sign on it, because with dollars it makes it super easy. What if I just drew this up here on the screen? These are there's 4 characters right there. They're not very well shaped because I got a shaky hand, right? But any of you guys could look at that, and if I were to say, hey, if you were to like enunciate that back to me, you would say that is $537, right? That's probably what most of you would say. But since maybe like 5th grade, have any of you really thought of why those characters mean 537, right? And I know, guys, I'm going all the way back to the start, to things that some of you never even think about because we just deal with this stuff so much it's easy to remember. If now that looks like a 1, that's still a 7. So you hear me say this thing, states of nature. How many states of nature can this occupy? Let's go look at the characters that we have. We have a 0, we have a 1, we have a 2, we have a 3, we have a 4, we have a 5, a 6, a 7, an 8, and a 9. We do not have a 10. We have a 0 through a 9. But that is 10 states of nature that this place right here can hold. Does everybody agree with that? Right? It's true. So it is a base 10 numbering system, meaning that there are 10 states of nature each of these can take. So if this is the first column of these, we're going to put a little 0 here because this is 10 to the power, oops, this is 10 to the power of 0, which is the same as saying it's the ones column. Because if you take anything to the power of 0, you get the number 1, right? That's what it equals. So this is the ones column. And then this is 10 to the power of 1, so it's the tens column. And this is 10 to the power of 2, and it is the hundreds column. Because if you take 10 times 10 times 1 is 10, and 10 times 10 is 100. Does everybody agree with that? So when we were talking about this, it would be accurate, it would be annoying, but it would be accurate to say I have 5 100s, 3 10s, and 7 ones of money. And you would look at me like I was having a stroke in the hardware store, because I'm like, look, dude, I don't care how you give it to me as long as it's $537, right? Just something like that. Anyways, my point in showing you that is this is the way that we are all used to dealing with numbers. Most, I would say most everybody on planet Earth, for sure anybody talking to me as an engineer, these are the types of numbers that we're used to using. But down here, we have a numbering system that is only allowed a 0 or a 1. So the states of nature here are all zeros, and all zeros in all of these places would equal 0. And if I put all ones in all of these places and then added 128, 64, 32, 16, 8, 4, 2, and 1, I would get the number 255. So, whereas here I can equal 0 through 9, 0 through 9, 0 through 9, I can have, in this case, I could have 999 as my top number, would be my top number. Here, the highest number I can get is 255. I doubt most kids would say 537. They'd probably say dollars. Yeah. It is interesting how things end up working. All right, so I'm gonna remove all this stuff on the top right because I think you guys get decimal, right? Like I'm not trying to reteach you maybe the stuff that you learned again in like probably 5th or 6th grade. But I hit that as a primer because that's where most of the rest of this kind of starts to look. So if you get stuck on anything and you go, oh, what the heck's going on here? Just remember this down here at the bottom is what's guiding us. This is, by the way, this sheet right here, I've been teaching off of this sheet for like 16 years at the college level. I have this up in our Discord if anybody wants it. I actually have old breakdowns where I give you a number here and then I tell you go break this down and then use, this is my method for breaking these down. You do not need, once you have familiarity with this, you can skip a lot of this. But this is the way that I show this originally, right here. Over here, I have the bits and the states of nature, because we might need those later, and I don't want to have to calculate them. We have some information over here about the classes of addresses that are common. There's 2 other types of classes of address. There's an A, B, C, and then there's a D and an E. They deal with the first octet as far as what they are, and their sizes, their general sizes. Now, you can actually break the rules on their sizes, but we talk about it in generalities when we teach things. You get to the nuance later. It's the same idea like I tell people, when you're a kid, I tell you can't cross the street. And you go, oh, I can never cross the street. No. When you get old enough and you understand how streets work, and you know that if you look that way and there's nothing that's going to come and squish you on the ground, then you can cross the street almost whenever you want. There's some streets you can never cross, right? Don't go cross the freeway. But as long as you understand, but I would even say if it was an emergency and you understood the rules of a freeway, I would be okay with you crossing. Now, I would tell you don't do that often, but my point is we tell you not to do things until you understand the thing, and then you can do stuff. So, all right, all that to say, this is a quick binary rundown. I'm going to show you guys, I'm just going to take like a number, like 10, let's say 16, 47, I don't know, 102, right? This is just some number. And let's say it's a slash. This is a, by default, 8. I know that from this. And let's say that we have like a 12 here. All right. There's a lot of things here. There's a lot of numbers happening, a lot of things. But this right here, is what I said earlier, is a dotted decimal notation, and each one of these represents one of these 8-bit components over here. So let's take this decimal number and break it down into binary. We've got a decimal number that's existing in that ones and zeros and all that stuff that we were talking about earlier. It can be 0 through 9. And let's turn it into this number that can only be 0 or 1. So this should be good. So we're going to mask it here in a little bit, in a second. So 10 is going to come down here, and we have to ask ourselves questions. We have to look at 10 almost like it's a little sponge that we can wring out. Let's think of it like that for a second. If I have the number 10, and I say, hey, can I squeeze 128 out of a 10? Can I shake my head like this and you guys go, are you insane? We're making it up, Shadow Developer. The 12 is made up. And this is why I say that. Because somebody in your company, before you ever got there, is going to make this number up. And then we're going to have to decide what to do based on that number they made up. I'll show you this. What it really is a carving of the room. I'll jump down to something and we'll come back to this, because the question came up, why are we doing, they're borrowing 4 address, they're borrowing 4 because it was 8 originally. But let me show you why that is. Hold on. Why do we subnet? This is the question, but Shadow Developer, hopefully this will help clarify this, because this is my explanation. This is how I show people what subnetting is, right? You're given a network address, let's say 192.168.1.0/24. That's 256 total addresses. 0 through 255 is 256 states of nature. You cannot use 0 on the ruling that the very first number is like the number on the side of the door that says this is the room or the network 192.168.1.0. So you take that one away. The last one, which is a 255, you're also not allowed to use because it is like you're yelling to everybody in that space. So this is the location of the space, if you want to think of it like that, and this is the yelling at the space. This is why we have or what we call the broadcast. This is why we have, you always take 2 away, right? All right, hold on real quick. So we come down, and I say, well, what if I was Scott here, and I was talking to my college students, so I'm over here, right? And I'm yelling at my college students. And another college professor I know is over here, and he's yelling at his college students, right? Because we have to yell at our college students. They're not going to yell at themselves. So here's my students, and here's his students. And when I go to yell in this network, what do I have to yell at? 255, right? And when he goes to yell, what does he have to yell at? 255. Well, doesn't that mean that we're just going to be talking over each other? Could you guys imagine if there was like another streamer sitting next to me and I'm doing this and he's playing Fortnite and nobody would listen to anything. Nobody would understand anything. But this is why we borrow bits. So, whoops. I'm going to take this network here and I'm going to borrow 1 bit. I'm going to borrow 1 bit on the far left of this octet, and this is what's going to happen. So you guys have heard of borrowed bits, but maybe somebody's never showed this to you. Yeah, is there anything louder than 255? That's funny. So what'll happen is this is my drawing. If anybody needs this is up in Discord. When I borrow that 1 bit in the far left location of this, now I have a /25 network, and it splits that network in half. This is the same as if you guys have ever seen like a big ballroom at like a crescent ballroom or something, and then they've got those things through the ceiling and they can pull the walls out and they can split it, so you've got a group over here and a group over here, and you can hear the parties on the other side, but there's like this little faux wall, and they can split that room further and have dinner for people and all that stuff, but it's a big giant room that can be cut up in different ways. That's what we're doing with networking, guys. That's all networking is. It's a mathematical wall. It's exactly what it is. So now when I yell here, I yell at 127, and I get all my college students in here. It's exactly like one of those, they kind of hang off the ceiling like curtains. They're movable partition walls, exactly. So the only difference in this is once they're set in the network. What I'm showing here, by the way, guys, so the way I'm about to show how this is carved is called fixed length subnet masking. I'm making all the numbers the same all the time. Yeah, digital Mason, that's fair. But when you do variable length subnet masking, you can go carve in to each of these different rooms if you wanted to in different ways. Yeah. I'll hold off for ads for a second because I know people got ads, so we'll hold on a second. I think it's like another minute over on the Twitch side. Yeah. So this is the way I think of it, because obviously I've been yelling at college students for a long time. But now I can yell at my students in each of the different rooms. All right, they got another 40 seconds or so over on the Twitch side, so we'll give them a second. Twitch gives a lot of ads. It's the nature of the beast, right? So we'll hold on for them. I don't think YouTube, I don't know if they give you guys ads during the talk or whatever, but then it'll go. Yeah, I think it's like 30 more seconds for the rest of you guys. So we'll give it a second. But now I'd be yelling at 127 here, and then he'd still be yelling at 255, but he would be in room 128 now. I'm still in room 0, and he's there. Okay. People should be coming back from ads in about 10 seconds, so I'll give it a second. I'll give it another second or so. This is the way that I kind of have shown it to students for a long time. This is the way I like showing it. Now, this is good, but this is still inefficient. I will never have 127 college students. Alex, yeah, I think on the Twitch side, people can do ad blockers for sure. I do have to say, as a Twitch streamer, I'm not allowed to advocate that stuff, but I am as an open source enthusiast and as an engineer and stuff. I do like to tell people there are tools for all kinds of things. I can't advocate those tools while I'm streaming or they'll kick me off. Shadow Developer, I'm going to show you what that 25 represents in a little bit. Well, I'm going to come back to that. I'm actually going forward to show you this, and then I'm going to go back to that decimal stuff for a second. But let's say I wanted to make this more efficient, right? And I'm going to further subdivide this to a /26 now. Yeah. So here, now I'm yelling at the 0 to 63. So now my yelling is at 63, but there's a 64 room and a 128 room and a 192 room. And this starts to get where we're also cutting through these different things. So this is where the numbers come from. This is why we do it, guys. We're trying to subdivide and more efficiently deal with the way things talk and yell, if you want to think of it as yelling, in a network. All right. So knowing this real quick, let's go back to where we get these numbers from. I'll go back up real quick and show these numbers again real quick. So I just made this number up for the purposes of this talk, but let's keep walking through some stuff here. I want to do the binary conversion of 10, like a little sponge, down to this is decimal, and I want to make it binary. So real quick, we're going to do it fast, but I'm going to keep saying it, and it'll get annoying to some of you, but to some of you, it'll click after you see it a few times. So watch this real quick. 10. Does the number 10 in decimal, 10, does that have 128 in it? Can I squeeze 128 out of this? No. Can I squeeze a 64 out of it? No. Can I squeeze a 32? I know this is silly to some of you. Is there a 32 in it? No. Is there a 16 in it? No. Is there a 1 in it? Yes. So I will turn on the 1-bit, the 8-bit. Sorry, I said 1. Is there an 8-bit? Yes, there is. In this positional place, I can squeeze an 8 out of it. So now I've got 2 left over. Can I get a 4 out of a 2? No. Can I get a 2 out of a 2? Yes. And then what do I have left over? 0. So the graphical representation in an 8-bit dotted decimal for the number 10 is 00001010. And if nobody's ever told you why, it's because there's no 128s, no 64s, no 32s, no 16s. There is an 8. There's no 4. There is a 2, and there's no 1. So it's 00001010. 16. Does 16 have a 128? No. Does it have a 32? No. 128, 64, 32. No. Does it have a 16? Yes. Is there anything left over? No 8, no 4, no 2, no 1. You guys see that? If nobody's ever shown you this before, this is very abstract. But once you see it, you're like, that's what these guys are getting paid a bunch of engineering money for? Oh, gosh. Like, like there's a cabal that's going to run me down for showing this to you. All right. No, I'm just kidding. But 128, is there a 128 and 47? It's silliness, right? I can't squeeze it out. Is there a 64? No. But is there a 32? Yes. So some people like to draw it like this and then say, okay, there's a 15 left. Is there a 15? Can I squeeze a 16 out? No. But fun fact, what's 1 less than 16? 8, 4, 2, and 1. Right? So 15 is an 8, a 4, a 2, and a 1. All right. So 102. How does 102 work? Well, does a 102 have a 128 in it? No. But does it have a 64? Yes. So I take 64 up there. I make that a 9. I make that an 8. I make that a 38, right? Take that away because that's gone. Is there a 32 and a 38? Can I squeeze out of a 38 the number 32? Yes. So there's 6, so there's no 16. There's no 8, but there is a 4, there is a 2, and there's no 1. I'm not doing magic up here, guys. All right. There's something about this address that starts right here that I need to know. And it is that it is a Class A address. How do I know that's a Class A? Well, because down here in my rules, these are rules you just need to learn. In the first octet, we've got between the 0 and 127 number. So we can call this a Class A. And because it's a Class A, it's got 8 network bits by default. So 8 network bits means right here, these were going to be 8 network bits. And then somebody came along and borrowed 4 more, which means that this is going to be subnetting bits, S, 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 and S, which means that all these ones are how many host bits, right? So I'm going to show you guys some stuff real quick. So if you put a 25 to the left of the 128s and put plus signs between the rest, that might help some people. Like a 250, this would be 256 would be the next one. But there's no 9th decimal. So yeah, this would be 256, but there's no, because it would be 2 to the power of 8, but there's no, that column doesn't exist. Now I know what the 255 is, but that's when they're all on. I can't have another place over here because there's no 9th. I guess I'm missing what you guys are saying about a 255. I put 0 to 255 here because that's all the states of nature, I guess. All right, so check this out real quick. On the masked bits, there's a rule over here that I have. So we've got to figure out how many host bits we have. We have 8 network and 4 subnet. I got an equation here that said if I have 8 plus 4 plus H is equal to 32, I can do some simple algebra and take 12 off of here and take 12 off of here, and that would tell me H is equal to 20, right? Most of you guys remember that. Yeah, if you add them all up, it's 255. So the host number of bits is 20 in this case, which is going to help us later. And then one thing I say over here too is masking. Network bits are 1, subnet bits are 1, and H bits are 1. So network bits are 1 in our mask. Subnet bits are 1 in our mask. And then all these are 0 all the way out with all our host bits. So when you guys see it for the first time, it's good to see. But if somebody were to ask us in this network, what's the mask that I have to put into my Linux box? Well, the mask will be 255 because those bits are all on. This is a 128, a 64, a 32, and a 16, which is 240. And then that's a 0, 0. So the net mask for this system would be 255, 240, 0, 0. Right? Brazilian schools skip algebra, do they? Oh. I think I started algebra in like 7th grade maybe. I forget. All I know is when I went into high school, I didn't have to do any more math if I didn't want to. I had already done all the math for graduating high school. I did math for fun, but I mean, I didn't have to. All right. In 5th grade, yeah. If I had stayed in private school, I would have definitely done it earlier. But in public school in Arizona, I did it in 7th. And then I was all done. I didn't have to do anything. Yeah, by ninth grade, I didn't even have to do any more high school math anymore if I didn't want to graduate high school, which I thought was kind of funny. So, this is all of our base components that we need to kind of move on. By the way, I was pulling numbers over here for making things like, because people will ask you questions. College professors and Network Plus certs like to ask you questions like, if I had a Class A address like this, and then I borrowed 4 bits like I did here, how many subnets would I make? Well, I have an equation over here. So if I said 2 raised to the power of 4, right, 2 to the number of subnet bits, which is 4, then I have 2 to the power of 4. Well, I can come over here and say that's 16. So I have 16 subnets here. And then I've got this equation over here for hosts. So somebody might say, what is my number of hosts? That's 2 raised to the 20 equals. Well, I don't even have that answer here. So what I might have to do is go to Google and do like 2 caret 20. And that would tell me how many total hosts per subnet that I have. So in each of those different 16 subnets, I have this many hosts. And we can go throw it in Google if we wanted, but that's probably not the size number that you're going to run into with your, with a test where they're making you do this. They're probably not going to expect you to do that. But I do like to put this on the paper. Like when I took my CCNA I passed my CCNA in 2002, so that was a long time ago. This is like the kind of thing that I would dump on the paper real quick. It's a lot of hosts, per subnet, so it's a big range of my college students to yell at, right? But at the end of the day, these are all the things that we were doing right here. So now this number real quick, I want you guys to look at this number for people that are newer to this. 192.168.1.0/27. I would have 8 networks of 1/8 the original size. And I want you guys to just look at these numbers for a second, and then I'm going to take this exact example right here, and I'm going to go do that in my method, right? My method only seems slow when you're showing it to people or when you're doing it at first, but after you get kind of familiar with it, you just blow through them. You can like look at it and go, okay, I got it. It just takes a while. Look, the first times you play with these numbers, it looks like a lot of a challenge. But basically, I had one big network, and I want to break it up into 8 networks. That's going to be the challenge on the next slide. And then we're going to come back here and make sure. I thought class addressing was depreciated by CIDR. Yeah, you can use the CIDR, which is just the slash. Yeah, the classless indoor domain, a lot of times we'll just use a slash like this so you don't have to do the whole net mask for systems. But some systems do it, and some systems require... My shoulder kind of hurts. I've been wrestling 5 days a week, so I've been like, my shoulders are sore from well, I say wrestling so people don't think it's karate, but it's Brazilian Jiu-Jitsu. All right. So anyways, we come down here, and I say, let's break down that /27 address real quick. So we're going to do the same thing that we just did, but with the purpose of trying to build this right here. Is that fair? You'll still see it. Yeah. Like if I pull up a Linux box real quick here, watch this, guys. I pull up, this is one of these things I tell you guys all the time as engineers. One test is worth 1,000 expert opinions. Let's just say, do I still need to know? Well, in this case, 127.0.0.1/8. That's my local. This one is /24, and then they don't show. Yeah, they don't show it here, but they do show my broadcast address, which I could have calculated if I knew this. And then they show my Ethernet. Okay, yeah, like these are things that. Yeah, they're not showing it as the net mask in there, but it's that's the CIDR notation right there. But that represents 255, 255, 255, 0. That's what that represents. All right, so let's go break this down real quick. Let's get into this. Let's go look at all the steps that I need to do this. So I take my 192.168 1.0/27, and I've got to ask myself some questions real quick. And I'm going to ask the questions like this. In this first octet, which is 192, is it a Class A, a Class B, or a Class C address by definition? What is it? Is it Class A? Here's the first octet, 0 to 127, 128 to 191, 192 to 223. Which of these is found... I just spit all over myself. In my first octet right here. What are we dealing with here? I think you guys probably know, but it's a Class C address. So, before I even touch anything else on this, I know I have 24 network bits. I know that I can't touch this 192.168.1. In fact, for all intents and purposes, for everything that could matter in like a Net Plus type test, everything to the left of this would be the same. So I don't even have to deal with this anymore in the calculations. 192.168.1, unless they asked me a question to break this down into binary, we could ignore everything to the left over here. But we're not, because we're practicing this. It's a /27 though, which means that somebody came along, some architect or engineer before I got here, and carved up this network like this. This is what they did. They took 3 bits to be subnet bits, and that changed a bunch of things. So the mask is a bunch of ones right here. Right? These are all ones, I know because of this rule. And the subnet bits are all going to be ones. So we've got a bunch of ones. And then we got zeros. And if I were to convert these sets of numbers back using this, I would get the number 255, 255, 255. Ah, what is this? Well, it's 128 plus 64 plus 32, which is 224. And you could do that math if you wanted to. Yeah. Killa, hey, how's it going? So that would be our subnet mask, and that would be our CIDR block for the subnet mask. But now we can break down 192. And can I squeeze out of a 192 a 128? Yes. And then I have 64 left over. So that is the first one. There's nothing left, so it's all zeros. Then I've got a 168, which I can squeeze that out of. I've got 40 left over, so I can't get a 64. I can get a 32. Now I've got 8 left over, so I can't get a 16. I can get an 8. I can't get a 4, a 2, or a 1. Does everybody see that? Now, 1 is easy because there's no 128s, no 64s, no 32s, no 16s, no 8s, no 4s, no 2s, but there is a 1. So this right here, 192.168.1, is the network. We knew that already. But then over here, you've got these subnet bits, so let's count up all the subnets. I'm going to often tell you guys don't do this by hand, but when we only have 3 of them, we can. So if I took this and I counted through it, what are the states of nature that can exist? Well, they're this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There should be 8 of them. All I did was add 1 here each time. And then it would flip the bit over if it needed to, or it would flip, in this case, it would fill up and fill the bit over to there. That's all I did. So, yeah. Yeah, it's 8 total. Yep, by the way, it's this equation. I normally would tell you, like, if it was anything bigger, I would tell you use 2 to the power of s. Just count up how many s's there are. Okay, let's say in this case I have 3. 2 to the power of 3, there's a number 8 right there. So, guys, do you see how these bits and states of nature start to help you when you start to look at these equations down here? Now, we could count the hosts the same way. I could say in the first network, the host would be 0, 0, 0, 0, 0 through 1, 1, 1, 1, 1 all the way up here. And that would be a lot. Or, guys, I could do this. I could say it's 2 to the power of h, which is 32 of them, minus the first one that you can't use because it's the network. It's the name on the door of the room, if you think of it like that. And then the last one is the broadcast that we're yelling, which is here and here. It's all the ones in between that can be used. So how many subnets? 8. How many hosts per subnet? 30. Because you got that minus 2, right? You got to remember that minus 2 when you do the math. That gets people. Excuse me. Man, I'm waiting a second for break. Guys, I went to dinner last night with one of my buddies. I haven't seen him since my wedding. He came up to my side of town. He might have came, actually we were talking about, he might have came over one other time. But he and I, we went to this place. We took the wives. Both of our wives are named Julie, so that's kind of funny. We took the Julies to this place called Rustler's Roost in Arizona here. And they serve, we didn't eat it last night, but me and the wife are going to go out there and we're going to get some of our more adventurous family to go with us. They actually serve rattlesnake there. So you can get rattlesnake. I thought that was kind of funny. We didn't get it last night. I got this platter of food that was like way more food. I couldn't even finish it. Like I was surprised. It was like brisket. It was brisket and like 2 jalapeno sausages. But these jalapeno sausages were like, they were I think they could have been a meal themselves. And then there was all this brisket on my plate. They probably gave me like almost 30 ounces of brisket. I told the wife, I was like, she kept going like, oh man, you know, I had 8 ounces and you had like 24. And I'm like, I'm pretty sure that it was a pile of brisket like this. I couldn't believe the amount of food these people get. Yeah, but I could have had rattlesnake if I wanted. Yeah. Anyways, all right. So we're back to this. All these things here are just really references. You don't really need them. But I want you guys to see, like, there were 8 subnets here, right? And remember I told you guys I was doing this to show you the last one? So let's go, well, what are the networks then? If this is the 32s column right here. Well, let me get my little pen going again. This is the 32s column. So if I were to just to count these up, the networks, if I were to go here, I would go, the first network is the 0. The next network is the 32. The next network would be the 64. The next network would be the 96, the 128, the 160, the 192, the 224. Those would be those 1, 2, 3, 4, 5, 6, 7, 8. Those are my 8 networks. Over here, they would count up to, and you can cheat. Once you've done them all, you can cheat because the last one here would be 223. It's one less than that guy. So this would be 191. This would be 159. This would be 127. This would be 95. This would be 63, and this would be 31. Now, take a quick look at those numbers. Oh, and this last one here would be 255, right? Take a real quick look at those numbers, and one of two things either just happened. I either just caused magic, or I demystified a whole bunch of math, hopefully, for you. Look at this real quick. Look at this. This is what we just did. Look at those numbers real quick. They're the exact same numbers right here. Magic. I either just cast a spell and did magic, or I did mathematics, right? Like, it has to be one or the other. Either I knew that this slide was going to match to the slide afterwards because I cast a spell on everybody, or it was actually the numbers lined up because of the math behind it, right? And it's simple math. It's really, at the end of the day, it's just looking at numbers a different way than you originally learned how to count numbers when you were a kid. Yeah, and we call stuff like it automagically or mathemagically happened, but once you understand it, you're like, that wasn't magic. We knew that was going to happen. And you go, well, yeah, that's what happens when you kind of like demystify things and learn these things, right? So all this stuff starts to become important when you set up your systems. By the way, this is about as deep as you need to go. Right here, what I'm showing is about as deep as you need to probably go ever on the system side of things. You really don't need to get much more into this than, like, if you're doing systems engineering and even software engineering, you probably don't need to go any further than this. And if you're doing platform engineering, which is me in the high performance compute space. However, it's funny, this last few days I programmed about, it was probably about 50, 60 switches. And so I do a lot of switch stuff too. And when I say switch, I mean layer 2 and layer 3 switches. So I do that stuff a fair amount as well. But anyway, so that's that general idea. So let's get into, we'll do less of the math stuff now, and we'll do more of the how data are flowing around, if that kind of makes sense. Oh, let me show you guys one other thing that's really important here. There's a concept here. You say, well, how does my system know? So when watch this real quick. I go on this Rocky box, and I say ping let's actually ping 192.168.11.245, which is on a different network. My device is on 192.168.200.51/24, and I'm going to ping something on a different network real quick, right? And then I'm going to say arp-a, and I'm going to see that the devices that are in the network with me, these are the devices that are within my network, are all this 192.168.200. But I might ask you, this would be a good conceptual question, whereas we had just went in and looked at this real low level stuff. This is the practical part of it real quick. How does my computer know that this device 192.168.11.245 was not on the same network with me? How does my device know that? And the answer to that has to do with in the IP routes here. Let's look at a process. I'm gonna say something that sounds big, and it doesn't even sound big. It's just people hear it and then their minds shut off. We are gonna do what's known as the process of ANDing. ANDing of bits. And then people go, it's an ANDing. It's scary. It's ANDing. Hold on. Let's step back for a second. We won't do all the logic tests, but I'm just going to say, I tell you guys that I went to the store yesterday and I went to the park, right? I tell you all that. And then later on stream, you hear me telling everybody, I didn't go to the park. I lied to those guys earlier. I went to the store, but I never made it to the park. Wouldn't most of you go, well, he lied to us. He said one thing and another thing, but he only did the one thing. Does that kind of make sense to you guys? You go, well, that makes sense. Scott's a liar, right? Okay, fair. Where I'm going with that is, ANDing of bits looks just like this. Watch this. If my device wants to know if so we're on a 192.168.1.0 network, right? But I also told the truth, but in aggregate for like a truth table, I lied. Does that make sense? Like I told you two things were true and I ANDed them, so I lied. Well, when we AND bits, it looks like this. Check if it's deprecated on the internet, WAN, on LAN, not so much. So check this out. If we AND bits, this is just a simple mathematical thing. This is how your computer does all kinds of things. But the ANDing of bits looks like this. Is this and this true? Yes. Is this and one is analogous to true always, right? Is this and this true? Yes. Is this and this true? No. Right? So we could do that dance all the way down, but some of you are very quickly going to go, wait a minute, Scott. So in your network example here, this is almost like a little platform, and all the things that are over here are going to stay true. So this is going to be 192, and this is going to be 168, and that's going to be 1. And I would say, yes, keep going. And then you say, well, there's more platform, but those are 0, so that becomes 0. And I would say, yes, you just found how a device knows if somebody's on the same network with it. So if I were to, just real quick, if I had a 192.168.200, which is, in my network, it's 11 and 1, but it doesn't matter. And 192.168.200 looks like this, right? That doesn't change. That doesn't change. Right? But the 200 up here looks like this. 1, 1. Right? Like that. That's the 200. You would very quickly go, they're not the same. That's all it is. ANDing is just, and then it just compares. And if any part of this is not the same as the network that I'm in, it immediately knows you're on a different network. How do I get there? In the Linux world, I immediately use my default gateway if I don't know a route to get there. So my device didn't know how to get to 192.168.11.245 because it's not explicitly in its routing table, nor is its address, its general range. So what it did was it said, well, I can't send it out here. I'll go ahead and send it out here. Now you might astutely be aware that they're the same interface, but that's not the point. The route chose this one because of that. And it does a thing called longest prefix matching and some other things that matter in the networking world, and in the troubleshooting it matters a little bit. But in the case of this, my device immediately knew when I went to ping something else that it wasn't on the same network, and that's how it knew, was by the process of ANDing bits against its subnet mask. So when you go, oh, it doesn't really matter if I have the subnet mask right, absolutely matters, because it determines how your device can communicate. And if you don't get your subnet mask right in the network, you can't broadcast, and you can't talk properly, typically, with your default if you have a gateway or a default device, and then now all communication is going to be, if it even works, it's going to be very wonky. And wonky is the technical term. You don't want that, right? All right. So, anyways, that's why we do that stuff. All right. So OSI model. You guys have heard that data flows from your system from one level down to the next. These are like an overlay of like logical flow that don't exist. There's no hard, we're at the application layer, we're at the presentation layer, we're at the session layer of your system, really, until you get down into the transport, and then it starts getting handled by the kernel and stuff. But the transport network, data link, and physical layers are still just kind of overlays to operations that are happening. The reason the OSI model is so important, there's two reasons. One is if you understand it well, you know what components you can change without affecting other components. That's important if you're engineering, if you're building things. And two, if you're troubleshooting or teaching things. So like if I'm troubleshooting things and I know where they break and I know what the behaviors are supposed to be, I can figure out what's wrong in the system. And then for teaching, we could say, hey, we're just focusing on the physical layer right now to the exclusion of all other layers. And people would be like, yeah, but you're down here talking about the physical layer and the way that the bits are sent over the wire or over the airwaves. But what about the IP addresses? And I'd go, we're not talking about that. That's not, we could call that non-germane, or we can call that orthogonal. There's all kinds of things engineers like to say so they sound smart. But the point is that it's not part of this discussion, right? And that's what these models help us to do, is focus in on individual things. So we were just focused heavily on the networking portion to the exclusion of all others, because that's where IPv4 exists, right? So the OSI model exists to give us all of these things. So that's what all the rest of this talk is about, is these different layers. Let me check. Let me make sure I don't have anything going on. Make sure I don't have anybody messaging me real quick. Hold on. Oh, somebody had asked me where they find the labs on one of the other things. If you need to get into any of our systems, the main place to start is to go into our Discord. We have Discord with a lot of networking talks and Linux. We're doing networking right now, but we're a Linux group, right? We're a professional Linux users group. Let me give you guys that link here for anybody that wants to go hang out. It's always free. We've never charged anybody for it. We've been running this group. We'll be going on 6 years on Discord coming up this in August. And I've been running the group for 11 years on the actual 11 years of actually running the group outside of that. We've got events scheduled, so there's a writer's room coming up, and the Linux sysadmin course is going to restart in March. So some of you guys have been around and done that as well. Yeah, Hayes, yeah, you do have to know analog for a lot of that stuff too. I tell you guys a lot, if you guys like doing digital and analog signaling, the guy to hang out with on Twitch, at least, that I've seen, is Sid Heresy. He's pretty good. That's actually pretty close to his name right there too. And we raid over to him a lot during the week because he's on a lot when I'm getting off. So he's pretty solid. He does a lot of digital and analog. He does a lot of audio stuff. So that's a thing. He's great for that. So Shadow Developer, the Book of Labs will be in discount anytime soon. I actually have a discount running on it right now. Hold on. Let me see if I have it. Hold on. Let me see if I have the link right here. Let me make sure that's the right link, and I'll send it to you on the YouTube side. Hold on. I gotta go look. Oh, yeah, there you go. All right, I'm linking this only because I got asked. Boom, over on the YouTube side, that's the discount. That's like the $10 book, so people don't have to pay $20. Yeah, I think Sid's really good. I actually like hanging out. I hang out in his stream even when I'm not like talking and stuff. I'll just hang out in there. Hold on, damn it. Now I'm stuck on YouTube. I can't get my chat. All right. Anyways, that's the book. That's if anybody wants the book it's on sale right now. The actual book that we have. So, you guys want a Ranger check? Hold on a second. Where's Ranger at? Hold on. Ranger. Oh, by the way, we got a little website. That's kind of fun. And I think, for for the most part, it's working. I need to update the cloud the CloudFront caches on it because sometimes you get these little weird things. Let's see. Hopefully we don't get them. Yeah, you get it's weird sometimes, but it does tell you, and it's weird because then it caches and it doesn't do it anymore. So I need to go. There's a timeout cache I need to fix in there, but it'll do that for like a minute and then it'll work. It's kind of annoying. It's because I have the caching set incorrectly. Hold on a second. Oh, anyways, here's Ranger. He hasn't really moved, has he? He just kind of crashed out over there. Hold on. Yeah, there. Yeah, it's like a weird. This thing's weird, but there's Ranger laying downstairs. He's chilling. There's his big bed that we bought that wasn't as big as I had hoped. So then it sits on top of his other bed, and he sleeps on both of them. So he's a pretty chill little dog down there. Yeah, Hayes, you definitely need a breadboard. Yeah, so when I was in college, my one of my main professors, actually, well, one of the professors at my college wrote the book on electronics. And when I say the book on electronics, I mean literally, like, Hayes, are you doing electronics work? I bet you've heard this name, Wayne Tomasi. He taught at DeVry, so Wayne Tomasi was one of our professors. He literally wrote the book, and you say literally, yeah. The signals engineering book that's used at like literally thousands of colleges around the world was written by Wayne Tomasi. Yeah. So if you've ever heard the name Wayne Tomasi, he was one of my professors in college. He wrote all of these books, and then this is the main one right here. This is the one that like literally everybody's used. Yeah, this book is used at thousands of colleges around the world. I'm not exaggerating. There's a lot of colleges that use Wayne Tomasi's book, but this was a book that I used. And then the main professor that I had in college was like his understudy, which was Bruce Fredericks. So Bruce Fredericks still does networking. I keep in touch with him in the Phoenix area here, and he was like he's referenced in this book. But anyways. That's one of my college books. I have the physical book downstairs. Some of you guys know I actually have every book that I ever taught out of college or have gone to college for. I never sold any of my books back. I've kept them all. I have all kinds of old books. I just keep them all. I do give away, like when I do pleasure reading, like if I'm like doing like mostly I read like sci-fi and fantasy books. I'll give those book series away when I'm done with them. But like books for college and learning and stuff, I've kept every book I've ever owned. Because I'm kind of a fanatic about that kind of stuff. Guys, you know what kept me from being, well, the same thing that kept me out of being like a full-time electrician is the thing that kept me from being a doctor too. Like I was going to be an MD when I was younger. I'm colorblind, so I just didn't feel comfortable. Like I'm not any good with electronics, but it's funny, I can tell a lot of the colors, and I can get away with like for resistors, I can get away with like doing simple projects and stuff, but I would never want to be a professional because it's the same thing with being like a doctor. Like I did really good in med science in high school, and I was like, oh, this sounds like a fun path. But then colorblind wasn't really in the thing. And I've heard people say, well, you can get around it, and I'm like, yeah, but I don't really want to get around it. I don't want to like look in somebody's throat and be like, that doesn't look red to me. I couldn't do it. Yeah. Making circuit art where you just saw. Yeah, I could probably have got around it, guys. There's tricks, and I know that there's like red tinted glasses where I could like see some of the reds, but it's like a disability. I'd rather you guys feel sorry for me than I'm just kidding. I got it back in other ways. Oh, I also have terrible eyes. So I have like the worst eyes of any person ever because I'm colorblind and I can't see anything. But I got it made up in other ways, I guess. So let's talk about the why the OSI model is so important then. And wait, let's compare this real quick back to something I said at the very beginning, which was this. You will always have a sender, a receiver, a message, a medium, and noise. This is the simple communication model. It never gets simpler, right? Yeah, there's a lot of people, X-Metric, mostly guys, because it's mostly carried on the Y chromosome, I believe, at least from what I've read. Yeah, see some guitar pedals. Is that new? You can use a board. Yeah. So the company I work for, some of you guys may or may not get this reference. Some of you guys that do music will. My company that I work for right now is called Redline, And the motto of our company is red line goes to 11. And if anybody gets the old, there's an old, was it Slayer? Gosh, I can't remember. I'm going to get killed now. Somebody's going to be like, you should know this. But where he goes, but this one goes to 11. And that's like the whole joke. Some of you guys probably remember that, but this one goes to 11. And they're like, well, what, isn't that just like the same as 10? And he goes, yeah, but this one goes to 11. And it's like the other guy was talking like ratios, because like, look, some of you guys know this. If you have something that goes to 10 and something that goes to 11 and both of them are the top, you're really just going to 1, right? And then a percentage. Yeah, it's from the movie. Yeah, I forget. It was Spinal Tap. Yeah, it was Spinal Tap. That's exactly right. It was the movie of Spinal Tap. Yeah. All right. So how does data flow between two systems? Well, it starts up at the top and then it flows down through the layers, getting headers as the data flows down. In fact, I have it right here. Yeah, there's a header applied here. Up here, it's known as a stream of data. Down here at the transport layer, it gets a header applied. Then at the network layer, it gets a header applied. At the data link layer, it gets a header, and for the first time and only time, it gets a trailer. And then at the physical layer, it's just bits that are a flow of bits across either a physical medium or a what we call a free space medium or air. Those can be, we could break that down a whole bunch of different ways, but then on the other side, using the same standard protocol, it has to catch those bits. It has to be able to accept the bits, because what does it matter if I can shotgun bits out over here at 10 terabytes a second, not even bits, terabytes a second, but if this system can't catch it over here, what does it matter? It's useless. It's back to that simple communication model. You have broken the simplest part of communication, which is all these things have to work. So now we catch it over here, buffering aside and all that kind of stuff. We strip off the header. We compare the trailer to the data to make sure we can do cyclic redundancy checks. We can do all kinds of other types of redundancy checks at this layer, right? But for the most part, it's cyclic redundancy checks, or sometimes we'll do like a fragment free checking it, and that was more when we used to do when we had collisions on networks. We don't really have collisions anymore with full duplex switches. There's no collision occurring anymore. But back in the day, and if you ever run into a hub, the collisions could happen, and then we would look at the first 64 bytes of a frame to make sure that there was no error before we passed it on. Then we'd strip that off and we'd get the network, and at the network layer we would see all that IP address information, and then from there we would strip that off and we would go to the transport layer, and in those headers there's one type of address I didn't mention earlier that's also really heavily important. If we had been doing networking stuff, I would have put it in there. In fact, I've thought about updating this slide to have it. There's one other type of addresses that's really important right here. It's a layer 4 address called a port. Your system has 0 to 65,535 total ports that it can use for TCP, and then the same number of UDP. It's 2 to the power 16. You can't use all of them, but they're all there. And we use the ports to identify how the systems are communicating between the two systems. Now, those ports only exist at this layer. None of these other lower layers care anything about those ports, for the most part. There's a little bit down here where in the network layer we talk about there's a field in the header here that can discuss what transport protocol is being carried, and it can affect the way that the system carries it. Also, based on what we're doing at the data link layer, we can put an 802.1q tag on a frame, and then with the VLANs, because that's a VLAN tag, 802.1q, or ISL if you're in an all Cisco environment, we can then use that to prioritize and shape traffic. There's two ways we prioritize traffic: with traffic shaping policies and traffic policing policies. The way that your devices handle overage of traffic changes between if you do shaping or policing. We're not going to get into that too much, but that's kind of a thing to think about. But the point is, as we get into it, the data are flowing down, they flow across as bits, and they go up. This right here is one of these things where, like, this diagram is both, I want to say, almost like elegantly simple, and also the whole thing. This is everything, like us communicating here, somebody clicking the like a follow, which thank you for that. Everything that's happening is summed up right here. but the summary is almost too small, because we could talk. I've often said this, and people are like, oh, I'd pay for a stream for that, jokingly, I'm sure, but like I've told you guys, I could sit here and brain dump on each of these, and you could time me. I could probably brain dump in each of, for sure, these bottom areas for over 3 hours each without notes. I could just go. We could just sit on this slide for the rest of the day. That being said, this is extremely abstract, and what I'd like to show you guys is there's practical application too. So there's a free tool out there. You guys can go to Wireshark at any time. Wireshark, go download off the internet. This is a completely free tool. I'm going to say no for right now. Completely free tool. Pop up right here. And I can go grab any of these old captures that I have, and I can see all the information that's happening here between the communications of a system. I can look at an interface. I can pull up and see this traffic. So we were talking about session, all the upper layer data right here. This is then UDP, so we're using UDP as opposed to TCP. There's a dichotomy there. You've got to be one of those two things. Here's the source port and the destination port, as we discussed, and then other information that's in the UDP header. We're going to get to that. Then that gets packaged up into an IP header. IP header has the source and the destination information held right here. Here's the source address and the destination address, and they're over there in hexadecimal, right? So these are the actual bits that are happening across the frame here. They're being shown in hexadecimal though, right? Then here's the Ethernet header, and the Ethernet header and footer that are put on the system are the these are the MAC addresses, and then where things are going. And you've got the globally unique, which is the first part, and then the individual address, which is the last part, right? So then you've got your frame here. So there's all kinds of information that's being shown here that you can dig into. But I tell you guys all the time, and I tell my college students this too, just having this tool is okay, but being able to come in here and use the tool effectively is much more effective. So I can come in here and I can look at telephony. Let's say I knew that because of the fact that this is SIP, which is Session Initiation Protocol, means a phone call is about to start. And then I'm using real-time transport protocol, but not secure real-time transport protocol, right? That's what SRTP would be, but it's a real-time transport protocol. There's a chance that I can listen to this phone call right here. There are 2 phone calls in this, and I can actually pull up these calls, and I can replay the call back to myself. Right here.
This is phone 1. This is phone 2.
People were talking, phone 1, phone 2, and this is actually the data that were passed on the system. We can see the protocol that was used. We can see the payload. It was a G711U codex to encode that, which probably actually saved us. When you talk even on a phone call, there's a lot of dead air, even in the seconds between your breaths and your enunciation. Even when I'm talking to you guys, there's a tremendous amount of airtime here where I'm not talking. I know that sounds weird. You're probably like, this guy hasn't shut up the whole time I've been here. But there's a lot of time when I'm not talking.
This is phone 1.
This is phone 2.
And that's compression. That's all time that's compressionable within your codecs. Guys, you can go make a career out of writing and improving efficiency in codecs if you want. You can go dig there. I mean, you can go play in a rabbit hole for a long time about phone codecs. And there's people that deal in call centers and do hundreds of thousands of calls a day and deal with how much we can compress and squeeze a little more out of these calls. So there's a whole, that's actually some of you guys that have been around and know me. I got a bachelor's in network communication management, and I'm one of the last classically trained people that came out of DeVry in telephony, because there was a telephone, like telephony type, it was telecommunications management, and they were switching it over to network communication management. So I learned a lot of this, when I was in there, and I didn't, this isn't my career, right? The last 20 years, that's not what I do. But in my bachelor's and undergrad, there was a lot of this stuff, and you could go dig in, and in the open source community, there's a lot of stuff for you guys to go mess with here. So, yeah, so echo cancellation is received. Yeah, fair. This is just raw us capturing things, right? So, where I'm going with that is we could spend a lot of time, but instead of spending all this time for you guys, where I say, hey, come down here, and I am a hobbyist, so I would just like tag along maybe with some tea. Yeah. Well, I tell you guys, if you're hobbyists, there's a good place to hang out. Although our group, our professional Linux users group, the stated goal is to try to get you guys to be professionals to be professionals in this space. But I tell people all the time, if you just want to hang out and do Linux, like people are joining, which is always cool. We got like 3,600 people almost. We're almost official. Not quite official, but we're almost official. I'm just kidding. Anyways, that's a place where people can hang out, tell jokes, and talk. Mostly, the most important thing is talking with engineers like engineers do. I tell my college students this too. You know, if you come to school, like for people that are in my college, I am at like an engineer level the entire time I talk to my students. And you say, well, why do you do that? Are you trying to sound smart? No, it's got nothing to do with wanting to sound smart. It's that somebody's going to take their time to come sit in a class, and maybe this is the only time they get to hear how an engineer talks. Maybe the rest of the time they're doing roofing or they're breaking big rocks into little rocks. I don't know what people do outside of school, but what I can tell you is when you're in school, I'm going to try to stay at a level. And that's kind of, I try to do that in stream as well, although we do joke around. But the reason I do that is because, you know, time is valuable. And if people want to hang out and learn something, I try to at least make it sound like an engineer would talk, right? And that's important. Because that's how, Marianne said engineer talks to students, prepares them for real life work environment. Yeah, I do try to talk to people like I'm the tech lead or the team lead, because I have been the team lead everywhere I've been for the last 13 years. Yeah, I've been a team lead since the early 2012 probably. So, and when I say team lead, I'm never the manager, guys. I refuse. They've tried to make me manager for a long time, but I won't do it. All right. So we get down here, we see how the data flows. Let's go look at each of these individual pieces, right? Again, the goal of this is not to be network engineers. The goal of this is to be a primer for Linux systems engineering, right? So layer 7 has some higher layer concepts or higher level concepts. There's HTTP, HTTPS, DNS is occurring up there. A bunch of the common types of devices you might run into are your web application firewall, your reverse proxies or load balancers, your next gen firewalls. So this is up at the application layer. Things are happening, right? So if I go into my lab right here, and let's come over here and let's go to where do I have the K8S-1? I think I can get in there as my user, yeah. Namels, how's it going? Hopefully this stuff's useful to you. We are going through layer 7 now. So I'm on a Kubernetes cluster, right? Let's go to my Scott user. Let's go look at some upper layer stuff, right? So I can say on this box, kubectl get services, I think, and I could say kubectl, let's actually just say curl 10.104.222.195. Let's see if I can just curl that. And that one might not work. All right. So, oh yeah. I should be able to paint. I should be able to curl it by its actual individual endpoints, which are here. 10.0.1.246. This is going directly to the node, right? And that will show me the page inside my system. No, this is real. No, this is full stood up Kubernetes. This is 3 individual nodes, and then it's a kube ADM build. So it's not mini cubes. This is real. This is like a real, no, this is real Kubernetes here. This stuff. Yeah, so this is a real Kubernetes build. on Rocky 9.4. This is not, no, this isn't like a mini cube or like a K3s or anything. K3s, which is the real lightweight like Rancher one. No, this is a real Cube ADM, and then we run this. This is a back end to our web page and everything in the system. I run a bunch of other stuff out there too, but what I wanted to show you guys was really just that curl. And I can do HTTP, and I can use a different non-default port to see the Professional Linux Users Group information, which was built by one of our guys, Treasure, right? And that's, well, you know, obviously I only know people's online code names, right? But anyway, so we can see HTTP traffic's been passed. And then I could dig into that more. And this is just the raw HTML that's coming across, right? But we could go and we can look on the system. We could look at how the service is serving that up. We actually bypassed right here. We bypassed the service for front-end IP here, and we actually just went directly to the back-end pod. Or we could have went here and said, you know what, use the IP here, and then use its, so here, and instead of doing what we had done, we'll go 3001, and now we'll get the same thing. So you say, wait a minute, that, oops, and that netted the same output. That's kind of strange. Well, and it's difference with where we're hitting it. One, I'm going directly to it. The other one, I'm hitting the service that redirects to it. So at layer 7, there's all these things that can happen. There's HTTPS. There's DNS. So DNS is a great way. DNS is one of my favorite ways to troubleshoot things. So let's say this box right here was having problems. This server that I'm on, this Linux box. And I said ping www.google.com, right? And I just hit Control-C after 1. And I tried to ask my system to use a name, and it went out and did a whole DNS request right here to get an IP address. So if that worked, and then knowing what we know about this, there was a request all the way down here, all the way up the other side for DNS layer 7, and then come back and communicate, and then my device talked with layer 3 via IP, you know, via ping, to talk to that device. The reason that's an important thing to know is this. If something were to break, I can tell where it broke. So a lot of times as an engineer, you come in and something's not working on a system, and you have to try to get this system back running, and production's down, and everybody's yelling, and the whole building's on fire, and whatever. I could start to figure things out now. Let's say I couldn't resolve that name. Now I could, instead of trying to ping, I could say host www.google.com. See if I can find the host. I can do an NS lookup to see, is my system actually resolving? And I'm using the server 192.168.11.1, which is an internal one. But if that internal address wasn't able to respond, do I have another one? It's always DSN. Yeah, we have a little haiku in the server for that. Everybody here know what a haiku is? 575, right? It's a format. I'll show you guys this real quick. This is funny. DNS haiku. There's an old DNS. It's not DNS. There's no way it's DNS. It was DNS. 575, right? If you guys have never seen that before, that's how. It's actually really funny. Let's see, open image, a new tab. Yeah, there you go. So it's not DNS. There's no way it's DNS. It was DNS. That's a haiku 575. And if some of you are like, I've heard of a haiku, where have I heard it before? I'm gonna just go ahead and save you the trouble. One of the funniest things that I remember with haikus, there's a very masterfully done show called Avatar. The movie was terrible. I think the new movie is probably terrible. I haven't even watched it. But the show, which was actually surprisingly done on Nickelodeon in the early 2000s, it's absolutely a masterful. And anyways, one of the main characters, I think it's not Toki's the girl. What's the brother's name? He was trying to talk to these women, and the girls, there were this like girls group with a woman up front, and they could only be spoken to in 575. So they would only accept him talking to them in haiku, and it's absolutely one of my favorite. It's just a great show in general. Yeah, The Last Airbender. Yeah, the show was great. Really a fun show. Just masterfully done. All this stuff, yeah, Ahsoka. Everything that came later wasn't so great. Like, I tried to watch The Legend of Korra. It was okay. And then, like, all the shows that were made after it were terrible. But one of the first ones was made by M. Night Shyamalan, which you already knew was going to be bad, right? All right, I'll stop. But what happened over here? I'm missing. Yeah, bandwidth management used to be my jam. Build systems, turn them over to remote team, and they'd lock me out and mess with it and call me. Yeah. Yeah, local Ken, I've been dealing with that. I deal with that a lot in government systems where we give them a system, they accept it, and then it gets slurped up into the government system, and then now I don't have access to it to help anymore. So sometimes I'll have to get access to, like, remotely watch, or because here's the weird thing. I have a top secret clearance, but it's inactive, so typically that means you have to go get it all over again. It's kind of a hassle. But my boss also once held a secret clearance, so do some of the other guys on my teams, mostly from military stuff, and we're trying to get it to where at least one of our guys has top secret. So my manager's going through all the process. If you guys have never seen that process, it's a long, very arduous process of putting things in. But then once he has that, he can go on site and do things. Most of us, we still go on site. Like, I go on data centers that are cleared, or cleared, but I'm not read into the program, so then they have to put the little spinning lights on. If you guys have never seen a little spinning lights on and then them going unclean, like you're a leper walking through their little colony, that's what happens if you ever work in a top secret space but you're not read into the program. It's kind of funny. But anyways, we'll get back to here. I could note, now this is working, so pretending to troubleshoot when things are working is kind of a silly thing, but I almost have to tell you guys, like, imagine, right? Like, imagine this was broken, and then I could start to figure out, well, is my DNS resolving? Yes or no? Is my route table working for that resolved name? Do I need to, add more resolvers to, it's like I have my local resolver, and then I do have a fail out resolver, like one that I should go to, but sometimes these don't fail over automatically. They always only try the first one. So, and then you can actually set here in the etsyresolve.conf timeouts and failovers if you want. So, and you might say, well, if I always have a timeout and a failover, and my system will always within 15 seconds respond back to that ping, 15 seconds is nothing to us when we're sitting here talking. Like, 15 seconds passed while, I'm sitting here talking about 15 seconds. But to the system, if your application was trying to resolve DNS and it was taking 15 seconds, that might as well be like 17 years to your system. That's well past any timeout for the most part. I mean, but you see what I'm saying? Like, you've got some application going along, and then 15 seconds to get a response to move on. That's too much, right? So yeah, that's exactly right, Hayes. It's 14.99999 seconds too long. Yeah, it's too much. So, but for us, I mean, we might look at that and go, that's not that big deal. Does anybody here remember? I think it was last year, the guy that had been working for like 2 years to get this stuff passed through all the code so that he could, like, backdoor every Linux server on the planet, and some dude caught him because his SSH sessions were taking 0.5 of a second longer. Did you guys hear about that? Some of you guys probably remember that. We talked about that in the Discord when it happened, and there's a bunch of links and stuff to it. But there was a guy who, he was using, like, this compression protocol, and he was doing all these separate commits, and he was worked up. He was right at the last stage to get that basically pushed everywhere on planet Earth, and he was going to have a backdoor. And some guy was, and we call this, like, and look, for lack of a better term, people called this weaponized autism, where some guy was watching his stuff and going, why is my system just half a second slower? And he dug in and caught this, and he goes, what the F is this doing? And he shut it all down. He started just, like, he was like a little, like one of those, you're trying to sneak around in a video game, and the little ocular boss comes along, or like the little guy that's pathing, and he sees you and he alerts everybody, and you're like, damn it, now here I go killing again. It was supposed to be an in and out mission, but now you turned this robbery into a murder. Everyone, okay, all right. In game, I have to say in game. That's the only way it's legal. Yeah, some of you guys read about it. The pager bombs. Yeah, that was a big one too. Okay, so we're looking here at how the data flows, and really we're down here just at layer 7, right? And we're talking about HTTP starts at the top. All of them still kind of as requests start at the top, but your different protocols operate up there. So HTTP, and especially when we talk about, in my world, coming from networking and being a web firewall guy for a long time, the things about firewalls that operate at layer 7 is they're aware of like the header information, right? They're aware of, as we pass like a call to, hold on, let me pull this up here. This, right? When you look at this is my call to my internal network here. And this is the IP address. This is the port right here. And then this is the path, right? This is the path that it's taking. So /d/ whatever, which is the actual name of this is a Grafana page in my home lab here, right? And then we've got this question mark, and we start to get to org ID equals 1, ampersand, which is and, from this time, and to this time. So there's 3 pieces of header information that are passed. There's also this full path information that's passed. And when we talk about like a firewall that is layer 7 aware, what that means is this firewall is aware of the things that it's protecting, and it knows that like if you're coming in on this IP address and you're using this port 3000 to access web, you probably will be using some, and sometimes it'll cache it, some number of headers that are common. Maybe these are all my common dashboards or whatever. And then maybe it knows the org IDs that certain people might come from. It's aware of things, is my point. A network layer firewall doesn't give a crap about anything above IP addresses. It's source, destination address. There's there's a tiny little bit of transport information that's passed down that it can care about with TCP or UDP at this layer, even though that's technically a transport layer. The header information or the protocol information is passed down, so network layer knows about it. Source and destination, so it's source and destination addresses, right? IPv4, IPv6. It's source and destination ports can actually be cared about here, even though they're up here typically. And the type of protocol, so TCP, UDP, and ICMP, those kind of things we could care about. So the reason I bring that up is sometimes you might have to configure those. Sometimes you might have to build those. Sometimes you have to, in our discussion, in our Linux sysadmin course, we actually got into this. So let me pull this question up real quick, just so you guys can see. So I'm always trying to tell you guys the Linux sysadmin course is free. Like, I'm selling it to you, but it's free, so you could just go do it. One of the questions I asked here early on, and I hope all the guys who did it, I think all the guys who did it caught it. I was asking a question about this. Where is it at? Pretty early on when we got into firewalls. Not that far back. Hold on, it might have been like week 5 or 6. Hold on. I just want to show you guys this real quick. So you fix a firewall here, and then you become the firewall expert here. That's kind of actually funny. That's funny if any of you guys are in the IT field, because you'll remember or you'll know, hey, I did something good once. Now forever I'm that guy. I'm that firewall guy, or I'm that systems guy, or I'm that. Oh yeah, no, don't go talk to Scott. He troubleshot that voice over IP problem with those guys. Oh, on a night call 7 years ago, late at night, and Scott got it all working. Scott's the guy forever, and you're like, oh, keep my name out your mouth. No, I'm just kidding. but like, you're gonna be the one who will always be talked about. Anyways, look at this. This one says the manager heard that you were the one that saved the new application by fixing the firewall. So you actually had to fix the firewall in this one and add a bunch of stuff in. But down here, they're getting pushed to do a web application firewall, which is a layer 7 firewall, in front of their application. You're the firewall guy now, and they're asking you to give them a review between the difference between firewalls, like a layer 4 or layer 3 firewall, and this one, which is a WAF. And you're like, oh god, now I gotta go write a paper, right? And that was part of it. And then we had a discussion, and people went and wrote things up. And this was what our Linux sysadmin course was all this stuff. Hey, IOFault, how's it going? Robodom, I saw you were dropping messages everywhere. I appreciate that. So again, guys, there's so much deep stuff that we can dig into here. But then also, this goes back to, this is going to be bright for a second, but back to this, I can understand what's going on here. If I don't think I have any HTTP here. Let me open. I think when I was doing PCAP, one of these ones. Here's some HTTP traffic. So something in my system was doing something. And it was talking to, let's go see if we can figure out what was happening in my home cluster here. It said that 192.168.11.245 was talking to 192.168.11.180. Now 245 is the box I captured this on. And that is this guy right. Hold on. That's this guy right here. He is 192.168.11.245. Boom. He is this source address. And he was pushing information to 192. So let's just grep let's go 180 in etc host. So who's 180? Well, he's my Loki server. He's also InfluxDB as well, but he's my Loki server. What does Loki do? On Loki API v1 push with HTTP 1, I can push information into that server from a log file. And here's my hypertext transfer protocol. And here's what I actually pushed over. There was some fill data. I may actually be able to go read what was in that data here, because it's not encrypted in any way. I was just pushing data over. Okay. And I might be able to, there's my full request URI. Content length. Here's all my data. I could probably go pull all this data out of there and go drop it in like an ASCII converter and figure out actually what was being sent, because it was just a line of a log, right? But the point is, I can see, yeah, all this information happen. Yeah, the Alice talks to Bob. That's the old as RSA was coming in, right? Was it RSA? No, it was PKI that was based on that. But so what was I doing with that request? I was pushing something over. So if I go look at Loki, so I SSH maybe over to Loki. Let's just say that box. And then I go, okay, that was pushing traffic. And let's see how it was pushing. We should be able to see the ports it was using. Oh, hold on. I gotta scroll down on our thing. The destination port that I was pushing to was 3100. I see that inside of my TCP connection. My source port was 44,250. That's an arbitrary port, guys. That's a port. My machine just went like roll the little lottery and the thing fell out. It was just an open port. The destination port, which is 3100, should be being listened to on this machine right here. Well, if that service is still up. So ss-ntulp grep for 3100. That is this process called Loki. I can go figure out what Loki's doing by doing something. There's a few ways, but lsof-i colon 3100. And here's all the things that are connecting. Look, a bunch of my different servers are connected back to that and talking. So that's awesome. In fact, all those servers that got cloned, they all have traffic being pushed in here. So then, in theory, Grafana should be able to go look at all the Hammer servers because they're all pushing in there. But they're all talking back on their arbitrary return ports as well. But they're all talking to port 3100. Okay. And then I may say, well, how did that service start? So systemctl grep-i for Loki to maybe find it. And then I say systemctl status loki.service. There's Loki. It was started as my system came up. It's active running. Its main PID is 688, which some of you may have caught was actually the process ID right here, 688. I can see what systemctl cat Loki. I can see how it was called. This is actually the startup service that System CTL or System D is actually the name of the daemon used. X Shunya said, "Where's packet filtering done?" Packet filtering is typically done in the kernel, and we could dig in. We could do a lab. We could dig in on packet filtering if we wanted to. There's a couple different tools that you can do to set packet filtering. Typically, we used to use IP tables, and then now it's NF tables, and that's going to be how we interact with the kernel and what's allowed or not allowed. The way that we watch those in real time tends to be with TCP dump, and then we do TCP dump out to like a PCAP file, and then we can look at it like this. Or we use like ngrep, and ngrep is a way to in real time look at kind of what's going on inside of your traffic coming in or out of the system. All right, so my point in showing you guys this was like we could capture traffic over here, we can look at it, and then we can go validate on the systems what's kind of happening, which is, I tell you guys all the time, like this is the same thing I tell my college students, like it's not all theory. Like this is all theory that I'm talking here, right? Like I'm just talk. But then there's practical, like hands-on. You have to be able to dig in and use your tools and deduce and figure out things that maybe are like fog of war over here. We don't have a clear understanding of what's going on with it. Give me 1 second real quick. I gotta see if I can mute that for one. I don't know if that still came through for you guys, but I tried to mute it. Had to cough. All right. So there's all that stuff. Also, I need to eat something. I guess the wife did make me some food this morning, but I got all that brisket from last night. Some of you got did it. Yeah, well, I wanted to not have the full force. All right, that's layer 7. Layer 7, we talk about these things called proxies. You guys probably have heard a lot of the term proxy, and most of you probably have done like forward proxying, which is I jump out to a server, that server does the request to the internet for me, comes back to that server, and then it gives it to me. That's what proxy means, on behalf of, right? Oh, Robodom, were you not here? Oh man, we went to this place. Me and the wife went to this place last night that we didn't even know was here in Phoenix. Like I've lived in Phoenix most of my life, except for a little bit of time in the Army in Colorado, and then a little bit of the time in Iraq. No, there's this place called. It's called the Rustler's Roost, and this is where we were last night. And it looks like this, right? This is out back. We weren't in the back part. We were in the front part. Let's see if they have. This is the back. We were sitting inside, but let's see if they show like the drive up. The drive up this place is really wild, and if you get there later, like this is them barbecuing outside. They weren't doing that at this time, but when we were there, we got there early, so we drove up. But people later have to park in this lower parking lot, and it's like a really steep walk. Like it would be a really steep walk for, I would say, like an elderly person. They wouldn't even be able to get up there. Like it's an incline. They have a little stagecoach that brings you up to the thing, so that was kind of cool. Yeah. Proxies. Look, proxies themselves are not good or bad. Proxies can just be used for whatever, right? This is what it looks like inside. It's all like this type of wood, like rounded logs, literally everywhere. There's a slide inside to go from the upper to the lower stairs. And then you can eat rattlesnake there. Robodom, so if you ever come out here, we're going to eat rattlesnake. But yeah, we were in here, and like inside here, like this is you walk across, these look kind of rickety, and when you walk across them they feel rickety. But there's a slide in there. Like even an adult can just walk up and go down the slide instead of going. Yeah. Well, you don't eat live rattlesnake, I don't think, but I guess you can. I had these frickin' sausages were jalapeno stuffed. Yeah, I'm gonna go heat that up and eat that in a little bit. And the brisket, they gave me way too much brisket. These are not my pictures, but this is the place. So that's what it looks like out back. We didn't go out back. We were sitting like right inside here. I want to see. This was cool. That's the end of the slide right there. There's a slide right back there for the kids, and then we were sitting back back underneath over there. It was a really cool little spot. I had never been over there, and it's only about 45 minutes from my house, so it's not super far. And then yeah, that steer or whatever steer is just sitting up there. You want to battle a rattlesnake? Yeah, as long as I have some kind of weapon, I'll battle a rattlesnake. Sure. Yeah, there you go. Snakes are wild. But all right, anyways, Robodom, we'll go there. We'll go there if you ever come out here. All right, reverse proxy, guys. Reverse proxy is something happening on behalf of the things behind. So a lot of the time we are using a reverse proxy, but we'll call it a load balancer. Load balancer is the term that people think, but what it really means is you are being abstracted from my servers. You, as a person requesting something, are hitting something that can either answer or send it to any number of backends. Well, the reason a reverse proxy is so valuable, or a load balancer is so valuable in the industry, is this. If I can abstract what's going on back here, right here where my mouse, right here. Let's see if I can do my little drawing. If I can abstract this here, right? Like you can't see it happening. Well, what that means is I can take, maybe a third of them down for maintenance. And your next request, the next request that comes in, goes to one of the 2/3 of the working servers. And then when I'm done with this maintenance, I go to my next 1/3 maintenance. And some of you guys have heard like rolling updates and all these different types of things that we do in the server world. Well, this is how I can do it, and you are none the wiser or happy, right? This is what we want in the systems world. We want the customers to never experience outage because of our systems being down. So load balancers with a reverse proxy are one of the ways that we can hide what's happening in the back end. The way I kind of explain this to you guys sometimes, that's kind of visceral, and some of you will be like, oh, that's kind of a awkward way to explain it, but it'll make you remember it, is this. If I went to your house and you've got 2 kids, and I'm like, hey, I've got a letter here for your kid, I'm just going to go ahead and take it to their bedroom. You'd be like, nah, I'll go ahead and take that here, and I don't even know if that's going to make it back there, but either way, you're staying right here. That's what a load balancer does. Another way to say this would be, you don't have any business knowing what's going on back here. It's a layer of abstraction for us. It's a layer, it's like a control point, it's a choke point. It's not quite a bastion, it's a little different concept, but this reverse proxy here it tends to be where we establish, like right here, we tend to establish our WAF right here for people that care about WAF, web application firewalls. They tend to be right here before you get to the reverse proxy, and I terminate my TLS there. And then that's how we establish that you're talking to the right thing. And only the WAF can actually even talk back to the reverse proxy and get to the things. So now you have to come in through the front door to even get to this where my maintenance is happening behind. Yeah, a gateway server can 100% function as a reverse proxy. In the systems engineering world that I come from, and then the networking side, when I think of the concept of gateway, for me, it almost always means a change in protocol. It almost always means a change in protocol. So a gateway could be like, you're coming in on, it's almost always a change in protocol, and this concept of AS, which was earlier we were talking about, that's an autonomous system. So a gateway means you're coming into my systems. Maybe you were using ATM, which is asynchronous transfer mode, or you're using frame relay. My gateway gets a hold of it. On my side, it's all 802.3, which is your Ethernet 2 frame, right? Well, it doesn't have to be Ethernet 2 frame, but let's just say 99.999% of the world is an Ethernet 2 frame for 802.3, so that's what we're using, right? So the gateway is the place where your traffic ceases to be in your little traffic's frame buckets, or, well, in your case, let's say frame relay or whatever, and it starts to be carried in my buckets, which are the layer 2 frames, right? and they're not really buckets, but they're analogous to buckets. They're just strings of bits, but they've got a header and a trailer on them that make them, for lack of a better term, like a bucket or like a train car or rail car or whatever. So yeah, that's how I think of it. Yeah, users are yeah, users tend to be sad in my world too. I mostly deal. My users tend to be other sysadmins and then developers. Those are the people that I deal with the most. I'm going back to my NOAA project though. NOAA, NOAA, and NOAA, National Oceanographic Atmospheric Agency. I'm going back to that project, and on that project, I will probably be dealing with a lot of research scientists as well. So, which is fine. I don't mind. I just, it's you just got to know your audience, know who you're working with, and then that, because some people want more technical, some people just want it fixed. You just have to kind of feel it out as you talk to people. All right. So layer 7 firewalls deal in a bunch of things, but I tend to see them as unified threat management, which are just 7-layer firewalls. They're doing everything, right? We could think of them as martini glasses. Yeah, that's fair. Fair enough. Next-gen firewalls are application-level firewalls that are aware of what the application's doing, can adapt to various applications, users, and devices. Are there well-formed application requests? Are there multiple concurrent connections, what we call embryonic connections in TCP, where they're trying to establish more than they should? They're trying to do the old SYN-ACK attack, where we make your server allocate resources, but we never do the final ACK. So we used to do SYN, SYN-ACK, ACK. That was the 3-way handshake. We still do it, but I'm saying we used to do that as an attack. I'd send a SYN to you, say, hey, prepare me a place at the table. I'm coming to dinner. You'd say, table prepared, place there, and I would just leave you hanging. I would never send the final ACK and show up. So those resources would just be hanging there. And then I would just keep seeing how many of those I could send to you to make you take up all the places at your dinner table. And then I never show up. Nobody ever shows up, and it's just you and the host. You and the other host are sitting there at the table with like 16 spots because I took them all. I took all the reservations, but I never showed up. That is a SYN-ACK attack, right? Part of the 3-way handshake. And we stopped that exploitation by saying, okay, you've sent too many SYNs. You've got too many SYN-ACKs back, and that's SYN. And you've got too many SYN-ACKs back, and you haven't ever done your final ACK to keep it, to create the session. So that's a embryonic connection. I will only allow you to do 5 of those before I stop anymore. And I'm like, look, buddy, you want to talk to him? Send one of those effing ACKs, right? Anyways, by the way, you can see this happen back in our Wireshark. You can see this happen. I can go to like my TCP, and I can see if some of these discussions were already going when I started doing this, but I should be able to with like a TCP. I can also search in here for TCP, by the way. But I should be able to... Oh, was I even looking in the right place? There's an ACK. And then we close down the communication when we're done. Let's see if we can see the start of one. Push, ACK, push. Oh, and then you can also see those in the frame. As we go to look at the headers later, we're going to see these in there. Where's TCP? Those are all ACKs. I have one. Hold on. Let's go open a different one. This one will have it. So SIP is the Session Initiation Protocol. Then our Real-Time Transport Protocol. I might not have one in there. Hold on. Let me see where I have one of these. Let's do my Kali one. I think this one will have some. There's a lot of ARP traffic in here because we were doing some testing. I want you guys to see some testing. We could actually just capture one live if we wanted to. A lot of ARP traffic. One thing you can do, you can come in here and you can actually follow the stream, where's that? Follow TCP stream, and we should be able to see at the beginning. Oh, these all are SSH connections. Okay, but we should still, if we had captured that while it was running, and we had started at the right time, we would have captured the initial communication. Let's see if I have one of these. Yeah, we don't have. Anyways, you have to have the whole stream. You can generate them, right? The point of that tool is to show you guys that you can look at it. But next generation firewalls keep track of that kind of stuff for you, so you don't have to. And then web application firewalls. These are the ones that we have a lot of cloud providers that'll do this, and then you can put them in front of the web application. Nobody ever talks directly to your application anymore. Now they come in through your web application firewall, right? And they are aware of like the OWASP top 10, and they prevent those attacks natively, right? So here's the OWASP top 10 if you've never seen it. It is, I think they're generating a new list right now too. But the last update I think was 2021. And then there's the OWASP top 10, which are big, and then also the API version of this. So there's an API top 10 as well. And then they show you like 90% of all API vulnerabilities come from the top 2 vulnerabilities, which are broken application and broken authentication methods, right? And then they show you a bunch of ways to stop them. And if you're like some of my guys here, I know like Robodom, he's a front end guy. He does front end development, and OWASP top 10 is a big part of that, because any company out there that's doing any kind of front end web and doing any kind of real work in there probably wants to know that they're protected against. They want to be able to tell their clients, hey, our stuff is protected by, following and adhering to these best practices or whatever. So that's the thing about firewalls. All right, here's a web application firewall example. This comes right from AWS. You got users coming in, valid users, invalid users. Invalid users can be bots. I actually have a good friend who works for a company that does, they're like they do sales of like office stuff, and they just hit $1 billion last year for the first time in their web sales. So they're doing pretty good. And he gets valid users and he gets attackers. And then over here it talks about bad bots. Well, there's good bots too. There's bots that will scrape your site for other vendors that you maybe work with. So he actually doesn't just deal with bad bots. He does all their data analytics. He does all the traffic analytics through Google and stuff. And that's what Jared does. He's come and talked to our group a few times. And the attackers come in and, maybe 90% of his bot traffic is bad and he wants to stop those. Well, your web application firewall can be aware of that. It can be aware of the behaviors that you're okay with, aware of the behaviors you're not okay with. And this is like the whole bit of it. But it's like Amazon CloudFront in front of a load balancer. That load balancer can go to an API gateway, make calls against Lambda, and then it can go fix things on the fly. Because web application firewalls can be tuned on the fly. We can block things, our own rules. We can have allowed lists and denied lists. We can block by country. Like if I by law right now in the U.S., by law, I cannot do business with Russia. Did you guys know that? Like if you're an American citizen, you can't do business with Russia right now. Did you guys? Most of you probably knew that. You can't take money. You can't do anything that generates money for them. This is one of these things about, war happens and you're like, I was selling all kinds of warm weather clothes to Russians, and that was my thing. And now it's done. Yeah, you can't. Yeah, if you're you're breaking American law if you're doing anything with Russians right now. You go look that up, right? And that's not good or bad. That's just a thing that you have to understand. I mean, the good or bad part of that for you can be something that you go, argue with people on the internet about. But I'm saying for not you, Hayes, but anybody else. My point in saying that is we can't do that. So we might have to put them all on our block list. And there are allowed and denied lists within Amazon Web Services where you can go and block whole countries. Then there's SQL injection. And I always give you guys this example. I was working at a big insurance company, right? I was their platform lead. And we were taking API calls were coming across our web application firewall to a exposed API endpoint that we had. Common practice. Web application firewall terminates. We know that the customer is it was one of our vendors, and what the vendor did was they were giving us bank information about banks that could be charged for like the insurance stuff that they were selling, right? It was I don't know all of it and I couldn't tell you all of it anyways, but what I can tell you is we were sitting there watching this traffic come through, and I was the red team lead at the time, so I was running all the web application firewall stuff, which is actually funny. It really doesn't fall to a red team, but that's just kind of where it had been put. So like I was what I mean by that is I was maintaining all the internal scanning of our systems for threats. I was maintaining all of our external pen testers, and I was running our firewall, which was super weird. But anyways, web application firewall. We got a bunch of these in, and they kept getting thrown back as SQL injection, right? So we were like, well, what the hell? So we dig in, we pull it open. Me and I had another guy on my team that he and I would work together quite a bit. Actually, he was a security guy, so he wasn't even technically on my team. But we were getting stuff like, I'm going to make these names up. These are not the actual names. But like, it would be like select first bank. And then it was like, what was another one? It would be like credit, Union First of Columbus or something, right? It would be something like that. And does anybody here, knowing anything about SQL, know why these were flagging in the system? We were getting big, long API lists, API calls that were giving us a bunch of information in JSON format, and we were going and we were looking through, and we were getting like select first bank and credit union first, and like these. Yep, yeah, Strager's exactly right. It was exactly right. It was looking at select, which is an SQL injection call, and it was looking at union, which is a way of doing a call inside of SQL to join. Right? Is it union or join? I don't know, but whatever it was, yeah, it was giving us. Yeah, we were triggering on that. So what we had to do was a thing called typically like whitelisting. Whitelisting is the idea that I trust you a little more. Yeah, I trust you a little more than maybe I trust other people. Now, whereas like I've known Robodom for a long time, right? Like I've known Robodom even like outside of stream, like in Discord and stuff. We need to meet up one of these times at like the conferences and stuff. But like I've known Robodom at least more than most people. And if Robodom called me up and said, "Hey Scott, I'm gonna be over there in like 15 minutes," I'd be like, I've known Robodom, he could stop by. But so whitelist might be like he's got a pass to stop by whenever he wants. He's got a pass to say select first bank to my API. Other things cannot say that to that API. In fact, to be fair, other things can't even get past the TLS to talk to that, because that's what the web application firewall is doing. But this was the web application firewall dynamically finding something that, honestly, thankfully, it was doing it, because that means, like, if you've ever looked at things like when you talk about like false positives and false negatives, and then true positives and true negatives and those kind of things, you may early on say, "Oh man, that's so annoying. I can't stand that I keep getting all those false positives." Well, if you're getting a lot of false positives in any alerting tool, guys, you're probably checking your assumptions that were made when you first decided to do the check were either too broad or too narrow. And the fact that the alert it just keeps triggering on you it should almost be like your conscience telling you, "Hey buddy, you need to think this through again," right? So this was a good thing. Like, but otherwise, like if you turn on a tool and it just never alerts, how do you know it wasn't going to work? I was appreciative of this. It took us a little while to dig in on this, but it was kind of good. I'm wary of what kind of service WAF could do to provide against SQL injection. Well, in this case, all it was doing was making sure that you couldn't do any SQL injection. It was like, I'm going to take 2 strokes off of Jerry's golf game by taking all strokes off Jerry's golf game when I kill him. Who knows what I'm talking about there? That's from a... Wait, where is that? Hold on. Do I have that? No, I don't have... Wait, where's he at? Streaming. Co-working. Streaming. I have it set. I have my studio set up wrong. Hold on. There. I can answer that for money. Who knows what that is, guys? All right. That's I almost said Jay and Silent Bob. That's our Rick and Morty, right? All right. So, anyways, what happens at layer 6? So layer 6 is one of the ones that we don't care as much about, which is encode, decode, compress, decompress, encrypt, decrypt. There are a lot of things that happen at layer 6 that deal with the encoding and decoding, the compression and decompression, and the encryption and decryption of stuff. So when I was back, this is going to be bright for a second, guys. When I was here, and then I was looking at like let's say our module 5 capture, and I was looking at, whoops, we don't want any of that stuff. Session initiation protocol is how we set SIP is at, for lack of a better description. If I were just to say at a high level, it's like your DNS for phone calls, but SIP initiates a phone call between two voice over IP systems, right? So I can go look at my SIP initiation and then my real-time transport. What I wanted to show you guys was this, was I should be able to, up here, see the payload type here. So earlier I was talking about how you guys could, I'm telling you, some of you might be like, I really like audio engineering stuff. I actually enjoy like sound engineering and audio engineering stuff. I'm not good at it. The guys that are good at it, again, we mentioned Sid Heresy earlier. That's what he does professionally. I got into it in college for fun, and I like looking at signals. I think signals are fun. I think that like it's easy to generate waveforms inside of systems, and it's fun. But you could make a whole career around looking at how people's voices have been transmitted and then building more efficient what we call codecs, right? And the codec being used here is ITUT -T, and then it's a very common one, G711. This one is, guys, this one's all over the place. This one's probably one of the more common ones because it's lightweight and it works good enough. In specific industries, there are other ones that are better, but for human voice, this is kind of like how Ethernet 2 frames work, where they're good enough. It would be like if I had a whole fleet of like Chevy Malibus, and you're like, why do you have a bunch of Chevy Malibus? And I'm like, well, I got to have 4 people in the car, and I want them to mostly get where they're going. And you're like, well, why don't you do Volvos? And I'm like, well, a little higher price point. Don't care about the people that much. No, I'm just kidding. That's terrible. But there's trade-off, guys. Everything in, man, I have a buddy who's an economist, and you can't talk to him without him immediately bringing up the trade-off between things. Well, you think that's the way your life's actually working, but you are trading off. You are eating all the things you enjoy, and you are getting fat because of it. And you're like, man, I didn't know you were going to make this so painful. And he's like, no, you're the one making the trade. He's a coach for Brazilian Jiu-Jitsu as well, so he does that a lot. But everything he does is a trade-off, and engineering is no different. The G711 protocol it's not a protocol, it's a codec, may work for you 99.5% of the time, and that's a good enough one for you guys to choose. Yeah, but yeah, if you guys don't follow Sid, you really should. He's got a lot of good stuff. Yeah, Hayes, that's true. I actually, and I'm guilty of this too with my college students. Like, I'll show them signal engineering stuff, and like I'll show like a loss of decibel. And loss of decibel as signals travel and do what's called attenuation. Attenuation is simply this. It's the weakening of a signal as we get... I know, you guys couldn't hear me. I did that on purpose. It's the weakening of a signal. Like, if we were 5 feet apart and I'm yelling like this, you'd be like, he's yelling at me. And then if you moved 100 feet away, you'd be like, okay, I hear him at a normal voice because I'm yelling right now. And then you move like 300 feet away and you don't hear me at all because I'm down like this and you can't hear me, right? But my system could hear me and it would do it. So anyways, where was I going with that? Attenuation, right? Attenuation a system. I show how you lose decibels in a system and how attenuation occurs. And there's this rule of 3s and rule of 10s, which is really easy to learn so that you don't have to learn the calculus behind it. So as Hayes mentioned, like there's a lot of maths that you don't have to learn. Guys, you can spend your whole career being really good at basic things. I'm very good at basic things. I build Linux servers. I automate the building of Linux servers. They bring out new versions of Linux servers. I update that. I figure out how to secure them. And I use the same protocol all the time. And everybody's always like, oh, that's Scott. He gets stuff done. Guys, Scott doesn't remember how to do it. Old Scott figured it out. New Scott's just doing that. So, checks out. Oh yeah, Hayes, you would probably like talking with Ben. He's actually come and talked to the group a few times on economics. He came and talked to, when I say our group, guys, I mean our little professional Linux users group. It's a free Discord. We've got, this thing's probably wrong, but it says we got about 3,500 people. This time last year, we were still under 1,000, and then like we kind of blew up. But I like that it's kind of going slow because I want it to keep like that kind of same small, what's that called? Robodon, what's that new thing you've got? You got what is that share the love icon you've got? What is that? Robodom's got some kind of little share the love icon I've never seen before. All right, anyways, this is what's happening at layer 6. I'm going to go all the way back for a second to something we were talking about earlier. Encode, decode, compress, decompress, encrypt, decrypt. Go way back here. It's way back to the beginning. The sender puts a message via encoding onto a medium. So encoding, whatever encoding he uses on one side must be the same decoding used on the other side. If I use the English language here at approximately 120 words per minute cadence, you can decode it in the English language at approximately 120 words per minute cadence, or what, I don't know exactly what we're talking at. Probably a little over 120, a little under 180, right? Somewhere in there. But the point is, I am using that. If I switch to French, well, I can't switch to French because I don't speak French very well. But I would be encoding in French, and if you didn't decode in French, we're done. That's it. That's the rest of the talk. Right? Like my message is not going to be received by you. If I compress it, and to compress the thing, I use some vice clamps, and I squish it down, and I just squish all the material out the side. And on the other side, you don't have a way to bring the material back together and then decompress it. My compression was, well, ineffective at first because I probably damaged the original. But the compression of a thing must be able to be decompressed on the far side. If you encode on one side, it must be encoded on the other. Robodom, you don't know how you got the share the love. That's funny. All right. So anyways, so we're down here. And then if I encrypt something, you have to be able to decrypt it. Now, encryption becomes this whole totally other thing because encryption does have to be on one side and does have to be the same thing on the other side. But the way that we encrypt can be symmetric. So I have one key over here and you have the exact same key over there, or it can be asymmetric and I have one key over here that's private and or maybe I have your public key and I generate encryption from your private key, and then only you with your public key rather, and only you with your private key can decrypt it on this side. By the way, I also want to point out, if you're doing asymmetric keying, you also have a lot of time involved because it takes about 10 times more work to do that type of decryption from an asymmetric standpoint than to do a symmetric. So if I do something symmetrically and you decrypt it symmetrically, let's call that 1, and then you do I do an asymmetric key over here of your public and you do an asymmetric decryption with your private, that would be a cost of 10 as compared to 1, so 1 order of magnitude more, right? Layer 5 concepts, there's windowing and flow control. Windowing and flow control directly affect how layer 4 works. But windowing is how much you can send at any one time. And then flow control is how we acknowledge back how much has been sent. So windowing would be with like a TCP stream, because TCP streams always have to come in order. You can send me 8 TCP segments before you expect back 1 acknowledgement. That's kind of high. But when we do that, we reduce the amount of overhead. If everything I said, so if I sat here, right, and everything I said to you, I then waited for an acknowledgement before I continued. So I won't, until somebody types in chat, I'm not going to say another word. There we go. No, I'm just kidding. So I was kidding, Robodom. I was gonna break sooner than later. But the point is, if I had to wait for an acknowledgement for everything I said, you guys think that would slow down communication somewhat, right? It does. It slows it down quite a bit. So that's windowing and flow control. They exist at layer 5. We don't really touch them much. In the networking sense, we're almost all lower. In fact, from a primer standpoint, this is a systems engineering and systems admin primer. You don't really need to know much about those other things besides what I'm showing. You look like you were being said, yeah, Rodon, I wasn't going to stop until somebody said something. I just go off stream. No. So let's go to layer 4, right? Layer 4 protocols majorly break down into TCP and UDP. There are other layer 4 protocols. There's real-time transport protocols, secure real-time transport protocol. Now, they it's funny, they are the major protocol, but then they still use like UDP underneath them. So it's kind of interesting. But we have 65,536 total ports. That breaks down to 0 through 65,535. But you don't get to use all of them because some of them are selected for other things. We tend to use the first 1023, so 0 to 1023 are called the well-known ports. And those actually exist in a system, in a Linux system here. So any Linux system ever, services. And here are the well-known ports right here, all the way down to 1024. So right here, this is where it ends. And then it says, here's the other ones, right? And then these are generic. Now, you can override. You can just use a port. The name be damned, right? But there's some fun ones. If you're going to go take a Network Plus or Security Plus, you do need to kind of know these. You just should know. For sure, you should know like 80. For sure, you should know like POP. You should definitely know 53 as your DNS. You definitely should know your Telnet and your SSH and your SMTP, like basically all of these in the 20 range. You need to know those. But you probably, I mean, you really don't need to memorize other ones, like Echo on 7. I didn't even know Echo was 7, right? But some of these other ones are good to know, like in the security sense, you probably want to know what SMTP is, and SNMP rather. All right, there's one that's not even shown here. That's actually kind of my favorite. Does anybody here know what the Doom port is? What's the Doom port? It's from a game from the early 90s called Doom, and you guys go look up what the Doom port is. TCP is connection oriented. It's got that SYN, ACK that we talked about. Then we pass data over in sequential order, and then we have a breakdown. When we say sequential order, every single frame, at this layer, it's segment, every single segment gets acknowledged before the next segments send within whatever the window is that you're allowed. UDP is the exact opposite. You just shotgun it over as fast as you want. And if the other node's catching it, good. If it's not catching it, who cares? UDP just launches across the internet. Doesn't care, doesn't come in the right order. Yeah, portal to the next level, yeah. And then layer 4 is where TLS lives. So that's important to know. Transport layer security lives at layer 4 as far as this goes. Layer 4 segment, the header for TCP looks like this. It's got the source port and the destination port. It's got a sequence number. It's got an acknowledgement number. It's got any data offset, which deals with the amount of data after the header. Then it's got reserve. This is a reserve section of ports, bits that are not used. And then here's your actual, if it's a SYN, an ACK, a SYN ACK would be both of them on. A FIN and a FIN ACK would be if they're both on. If they're all turned on, we call that the Christmas tree. If you guys have ever heard of like a Christmas tree packet or segment, it means that everything was turned on, which tends to be something that people used to use to try to get past like firewalls or cause problems and that kind of stuff. There's a checksum at the front that helps tell you what the whole length of the data is. If there's any urgency for the pointer, any options or modularity that you've built in, padding, and then all of the data. The data starts with, the data portion of a TCP header starts with the all the data that comes from the above protocols, right? So this header gets put on the front of it. You can go look at these, right? You can go look at a TCP header right here. This is a UDP header. Let's go find TCP real quick. This is literally all UDP on that one. Hold on. We'll go look at one of our other tests. So here's a TCP header, and here is the source port, the destination port, any of the segment length, the sequence number, and this is interesting. They'll give you the relative sequence number, which means this is the first one, or the raw sequence number, which was the generated one that was actually used, right? Acknowledgement number, header, flags. So you wanted to know if this is just an ACK and a push. Those are the two flags that are set. It is not a SYN, it is not a FIN, it is an ACK. But it's, yeah, There you go. And this maps directly back to this right here, the actual structure of it. You don't need to memorize these kind of things. You don't need to really like dig into these kind of things unless you're having problems in systems. But this is a high level little primer for you guys on this. So, all right. Then here's the UDP header. So if I didn't tell you anything else about this, but you looked at these numbers and you looked at this, and then you looked at this, and you looked at this, and I didn't tell you anything else about these. And I know that the size isn't exactly relative, but I just want to show you guys these two real quick. Which one of these do you think has less overhead? Like, which one of these has a shorter little list of packing info with it, if you want to think of it like that? Which one of these do you think gets to the other side faster? Which one of these is used for more, more things? So just if you just look between these. By the way, this whole talk is recorded on YouTube, but all this is up in Discord. So if you guys need, like, I even have it at the end of the talk. I have all these, so if you ever need, like, if you wanted the images that go with this, you can have all that stuff. Or if you were like, oh, I want to modify that, I have them all at the end right here. Oh, wow, this is a long talk. At the very end, I actually have them if you need them. They're in a hidden slide, though, but look, there they are. If you needed to, you can go in and modify these. Somewhere, I have the thing somewhere you can modify. I don't know. Anyways, if anybody needs it, just let me know. All right. All right, let's go back to where we were. Yeah, so you would be right if you said this one is much more lightweight. This one has a lot less overhead to it. Yeah, this one's got a lot less overhead to it for sure, 100%. And you can go read. I tell you guys a lot of times, like, if you want to get into like network engineering, you got to go spend some time reading your RFCs. If you don't want to get into network engineering and you just want to understand this stuff, stick with your TCP dumps, stick with looking at your Wireshark, and just understanding the behavior of your system. I think there's some value to sitting around. This is gonna be bright for a second. I think there's some value to sitting around and watching what traffic is happening on your network. If you want to be a network engineer, you got to get used to how networks are traffic and how they're talking. There's also some really good, if you look at this, if you like capture your network for an hour at your company, you can come in here to statistics. This is actually really fun. You can go dig in to all kinds of information here. Conversations, endpoints. You can generate IO graphs of like what was happening if there were ever errors. But one of the ones that's really kind of like a high level, here's all your IPv4 statistics. And I just want to know, just go ahead and show me all addresses. Give me some statistics here real quick of like who's being my chatty Cathys, who's being my... That's funny. I never thought I'd ever use that expression in like a real. But this is like how much of my traffic is going where. And what if you found that a bunch of your systems were talking where you didn't expect them to? So you come back here, you go back to statistics, you go back to IPv4, and you just say all sources and destinations. So now we got our source and our destination. And what if I found out right here that all of my traffic was going to like some Chinese organization? Or some Chinese organization was talking in and they were getting responded to. And I'm like, oh, geez, I didn't realize 50% of my traffic was going out to whatever. Well, how would you know that, right? Like, how would you know that if you didn't track it? Now, you might say, Scott, well, is that really practical for me to just sit there and do like TCP dumps on systems? We have tools. There's open source tools. I would, if you say, Scott, that is a actual concern for my organization, like we really need to know this, I would tell you this is your way to kind of like, this is kind of like your doctor's office visit. You just run your scan in your network. You have to be on a promiscuous port. Yeah, 50% is traffic. Fair enough. Fair, right? My clusters that I work on, my high performance compute clusters, are literally all Linux from start to finish. And then once they get into the government DREN, they tie into LDAP. So I literally have no Microsoft traffic all the way until easy money. If you're listening to network traffic on your system, I would argue it's never illegal. But that is an interesting thing, easy money. I remember, this was probably about 15 years ago. and I don't want to look. I don't want to besmirch any country. Well, I do want to besmirch other countries. I'm American, right? No, I'm just kidding. But um, where I'm going is this other country. It was Canada. There was a guy who blocked his Wi-Fi and locked somebody else out, and that person had been on his Wi-Fi for a while, and he sued him in Canada, and he won, and that guy had to reopen his internet traffic for that guy. And I'm sitting there going, "There's no way. There's no way I wouldn't be able to do it." But if it's mine, well, if you're on a public Wi-Fi, if my system can, I would argue though, if you're broadcasting into my home, it's mine. But anyways, there's legalities there to that. I can tell you the FCC in the U.S. I know this because remember I told you guys I'm a network communication. That's my undergrad. But telecommunications was kind of my start. I happen to know that the FCC allows you to broadcast on any signal within 60 feet of your house. That's for testing purposes and stuff. So if I wanted to jam things inside of my house, I would be allowed to. Now, if that went out and affected other people, that would start to affect what's called Part 15 of the FCC's deregulate, because there's a bunch of deregulated channels that you're allowed to go on. You live in your car. Yeah, well, if you live in your car around my house, I'm going to jam you. So, Xmetric, you'd really like my buddy who's on our server as FaintCalf. He's a security guy, and he used to drive around all the time. All he did was war drive with his little Pi in his car, his little Raspberry Pi, one of these little things that would hang under his dashboard. And he would just gather all the networks, and then he would just go and he would upload it to a site called it's called like I don't know, it's like one of those ones where basically where all the free and open Wi-Fi's are everywhere. It's kind of what you would consider like kind of a hacker network of, if you were ever running and all your stuff was shut off, you could still upload your things at any of these places. That's the idea behind it. And he was like number 5 in the world on that site for like all this stuff. So anyways, I forget what the name of that site is though. I could look it up, but he'll tell you about it on Discord if you guys ask. He's pretty good about talking to people in there typically. Anyways, where was I at? Oh yeah, here. So then we get to TLS, right? And TLS is happening only on TCP, right? It's a TCP function. We can't do UDP with TLS. But the client and the server are going to introduce themselves. He's going to say hello, hello. He's going to give a key exchange, and then that one's going to agree and prove that he is who he says he is via his private certificate, and then he's going to decrypt the message that was sent. And this client's going to say, okay, I believe you are who you say you are, because only the person that had your private key from the public key that I used to generate this traffic would be able to do it. And then they'd get an answer. And then they would then, right down here, they would generate a symmetric key. They'd calculate a symmetric key, and they would use symmetric key encryption to talk the rest of the time. TLS and the asynchronous portion of it only happens at the beginning. Doesn't continue going on down through the connection. Wait, hold on, Xshunya. You said this at the top. You're talking about these. This is just the position of the bit. So this is 1 bit, 1 bit, 1 bit, 1 bit, 1, all the way down. So there are 8, 7, 8, 9, and then they start counting over. But the first 16 bits are the source port. Xshunya, if this is what you were asking, here's the source port is 16 bits. Destination port is 16 bits. So wait, come back here. When you look at the TCP segment here, here's the source port, which is those 16 bits, and the destination port is those 16 bits as well. So the source port and the destination port, if we were to break them down, it's B132. And we could break down what B132 is if you want. I'll show you this real quick. So that source port right there was, let me get my little pen out here. It was B1132. But that is in hex. Right? So what we saw in the TCP dump for this was B132. But it was in hex, right? So what that breaks down to is this B has 1, 2, 3, 4. This 1 has 1, 2, 3, 4. This 3 has 1, 2, 3, 4. And that 2 has 1, 2, 3, 4. So 2 is easy. There's no 8. There's no 4. There's a 2. And there's no 1. 3 is similar as well. There's no 8 and no 4. There is a 2 and a 1. 1 is easy because it's 0, 0, 0, 1. And then B is a little more complex because B is actually 11, right? Because B, you can't, in hexadecimal, you can't represent 0 through 9, but now you need those other ones. So then we have the numbers. They are numbers, A, B, C, D, E, F. And you say, oh, they're letters. When they're used in hexadecimal and they're in capital like they should be, they are going to be numbers, right? And this is 11, so can I get an 8? Yes. Can I get a 4? No. Can I get a 2 and a 1? Yes. So that's the number. Yeah, there's the number right there. Now, you could take that number and you could put that in a calculator. You could put it in Google, and it'll tell you that that maps back to that number. This is why, guys, this is one of the reasons Wireshark is so nice. It told us that number is 45,362 when you aggregate it up. And because the positional places keep going higher. 45,360. Yeah. So you guys, you don't have to memorize these from this standpoint. You can just use a tool. I can go right here. I can go off my standard calculator that I normally use for stuff, and I can go to my programmer calculator, and I can say hex. I could do any one of these, and I could say B1, right? B132. And it would give me that same number that we just, you guys are looking at my hands. You saw me do all this stuff. I didn't cheat and do that. That's where it comes from, though. So, yeah, and you have reasons to switch between these and understand the different ones. I mostly deal in decimal and binary, but hex is the way you see things sometimes. There's actually, InfiniBand uses a hex. They use a hex number, and then that hex number translates back to, let me think. Yeah, they use a hex number in InfiniBand for the SIDs of the devices and the things. So you have this big scan on InfiniBand networks, and all the devices kind of check in, and you can then use this number that is hex, but you got to convert it when you go to do like updates and stuff. It's kind of an interesting thing, but you would think that they would just use the same number in their actual tool, but no, you have to go convert it. So a lot of times we'll just use like a little Perl script or something to convert them all, or you can do them by hand if you want. But anyways, the point is learn your tools and learn how to like look at these things, and then when you have to go figure it out, you'll be ready, right? So Xshenya, hopefully that helps, because yeah, these are just positional places across the top that are part of the RFC. But for us, it's just a sequence. This is just line 1 ending, line 2 starting, line 3 starting, and they're just a stream of bits. All they are, right? InfiniBand, I think I read something about it when messing with oscilloscope. Yeah, so InfiniBand is the NVIDIA. So NVIDIA bought Mellanox about 10 years ago, and Mellanox. So a lot of you guys are like, oh, NVIDIA's got a stranglehold on like GPUs, and they do. But did you guys know that NVIDIA also has a stranglehold on all the fastest networking in the world? If you go to, Mellanox got bought by NVIDIA, yeah. So if you guys ever go here and go to top500.org, these are the, like, I work on these supercomputers. These are the types of systems I build in the government, right? In fact, some systems I built are still on here. And systems I built are coming out on there too. If you guys have never seen Top 500, you can go to any of the old ones. But when you go and you look at, like, this is November 2024, most recent one, you've got to run a LinPack on your system. LinPack is the standard. And then it's basically just the overall aggregate IOPS, right? And in this case, petaflops, the floating operations per second. And El Capitan by HPE Cray is the top in the world right now. Frontier, the supercomputer Fukagu, he came out in like 2020. And one of the things about this one that was so massive was he was the first time that ARM ever took #1. ARM is a type of chipset, right? It's used in these little guys, Raspberry Pis and other stuff like that. And it tends to be a lower There's lower power draw with them and lower power spikes too, because we spike power with these big time. But yeah, these are how we build our systems. There's a separate one in here too for people that care about being green. There's a green one, and it's the fastest, but with. Oh yeah, guys, these things are massive, but this is the one that's the most efficient for its size. So this one, the green ones start to get, I don't want to say wonky, but this is just raw. This is like, I'm at the track. How fast can I get this vehicle to go down the track? That's what these ones are. And yeah, a million cores, guys. It's wild. It is not. I wonder if any of the ones I worked on are still on here, because the last official ones that I did, if we go back to, it would have been June of 2021. And then once you get here, you got to download it, right? So let's just say I want to download this as, do poster in PDF. Let's see. Boo. Boo. You give me it as X. Oh, boo. You used to be able to just download these. Anyways, mine debuted on here as Dogwood and Cactus. This is a press release, so I don't mind showing it to you guys. But this was, yeah, we were earlier than that. We were in, anyways, Dogwood and Cactus this is Dogwood out here. So this is in Virginia, which I can tell you because it's there. I live about 3 miles from the Cactus system, so I helped build both of them. I'm the guy who wrote most of the Ansible in these guys. So, yeah, and they're water cooled. Yep, I was there for them putting most all that in. And then I left that project, and then I'm going back to that project again too. Yeah, Super HPC is the login. Yeah. Man, we have like CAC cards and all that. It's all like super government access stuff. I build the Bastion systems for those, and I show you guys how we build Bastions in the Linux world. We got talks on that, and I've got to finish one of those labs on that, but we've got labs on that too as well. Bug Me Not. I don't think I've ever played with Bug Me Not. Is that my risky click of the day? I'll click on that later. But anyways, we get down here and then we calculate. Here's some other things that are important. PKI is public key infrastructure. You can run your own stuff. You can trust other people to maintain them. Some people will build their own internal PKI. There are companies and tools and open source projects that will do most of this stuff for you nearly for free. You can run most of your PKI internally, probably almost every use case you can think of, off of a tool called Vault. So a lot of people love. Bug Me Not is shared logins. It's actually funny. Browsers use SSL and TLS. Can use HTTPS. Yeah, that's important. We ensure the authenticity, so you are who you say you are, and then we can also encrypt data when we go down into TLS. You don't use SSL anymore. You use TLS 1.3 typically. That's the current standard, even when I wrote this. SSL should be deprecated and removed everywhere as of like 2017. So you should at least be on TLS something. All right. And then this is how PKI goes. Normally I talk through this. It kind of looks like this, where you've got a certificate authority, and they will generate you a SSL certificate, and then from there you can generate a private key for your server. That private key stays with the server, and then your public key can be shared anywhere out. In fact, the certificate authority will give people your public key if they ask for it. And you can set in your browsers all the certificate authorities that you're going to trust, and that can be set within an organization, like when you deploy workstations and servers and stuff. And then they will trust, and they will get the public key, and then they will be able to encrypt and send something over to your server that only with their private key would they be able to decrypt. They'll be able to go back and say, hey, because of you sent me the number 441111, I decrypted it, I sent it back to you like this, and I would say, yes, that is what I sent you. Only the person that had the private key could do it. and then we would be able to talk. Now it's interesting, and then we would initiate our SSL or our TLS communication and generate our symmetric key. I've seen there's some really bad examples, and I actually don't like when people post stuff and then everybody sits around on like LinkedIn and stuff and claps about it, but it's like incorrect. But I can assure you, you never send your private key anywhere. There's drawings out there that show that the private key gets sent to the. It doesn't make any sense to send a private key anywhere ever. Private keys always stay put. They always are locked up. They're always encrypted. They're not always encrypted, but they're definitely sitting in a way that they can't be touched by other users on the system. And if they're ever compromised, we have to throw away all the keys that have been generated underneath that key, all the certificates that were signed with that SSL certificate or key. So we don't send a private key anywhere. If you ever see like very popular things on LinkedIn where they like to show all these things flowing and they show that the server sends you its private key, it would defeat the purpose of doing key stuff. So yeah, that's fair, Marion. You're welcome to just hang out here instead. We hang out here. We also hang out in YouTube. You don't have to do Discord if you guys don't want. I'm trying to think if we meet anywhere else besides Discord. We mostly just hang out on Discord. But it's one of those things where it's like, yeah, you know they're recording you, you know they're whatever. But, I mean, that's probably true of, like, every time you got your phone on you anyways. My wife had a really bad headache on Monday morning. I remember because I didn't get up. It was a holiday, so I was going to go to the gym early. And I didn't end up going because her head was hurting. And then all of a sudden I started getting all these alerts on my phone for, like, all my ads were like, hey, if you have headaches and, hey, if you've got high blood pressure. And I'm like, what are you talking about? I was talking to my wife about this stuff. So anyways, yeah. So we get, everybody's tracking all our crap. So layer 4 example in Wireshark, we've been looking at that the whole time. Layer 3 routing is two things, path determination and packet switching. There's a function of routing that is also there, which is access control lists and logic. And I call access control lists the coin sorter problem, because I try to make things, some of you guys have been around and seen me talk about engineering. I try to make things as simple as possible, but no simpler. That's an old quote by Einstein, in fact. Well, it's attributed to Einstein. Who knows if he actually said it, but it's make things as simple as possible, but no simpler. That's a pretty good engineering quote in general. So, and then there's also like IPsec tunneling, which is an important kind of concept. But routing deals with your source and destination address. This is 32 bits across right here, and this is 32 bits across. And everything in this source address is summed up in what we did earlier, where all we did was look at that. Yeah, my industry, I agree. Google is kind of creepy. It kind of does track everything you do. Yeah, I get really weird. So you guys want to know the one that bugs me the most on here? Is I will get stuff on Google. Let's say, so we were talking earlier. I went to a place called the Rustler's Roost last night. It's a little steak food place here in Phoenix. And I went there, and if they asked me today, would you like to do a review of Rustler's Roost? I would be like, oh yeah, that's interesting. I enjoyed it. The food was good. 5 stars. I would do that if Google asked me to right now. Right now, Google. Right now. No, but what's weird, and this happens to me a lot, is because I travel some for work. I probably travel a few times a year for work. I'll just get a message on Google, like I'll get it like tomorrow morning, and it'll be like, hey, when you were in Hawaii in November, how'd you like that one place? And I'm like, what the fuck are you talking about? That was months ago. But that's what's weird to me. That's the one that I'm like, that like got stuck in a queue for a long time before it came in. Cause like it's not weird if you tap me on the shoulder and we're like, hey Scott, what was that thing like 5 minutes ago that we did in networking? I'd be like, oh yeah. But if you were like, hey, Scott, I remember like a couple weeks ago you showed your address on stream or something, and could you show me that address again? I'd be like, that's a little weird. I don't show my address on stream, or I try not to, right? Not because I worry about anything, but it's just, it's one of those good internet, society type behaviors, and it's good security posture and that kind of stuff, right? It's actually funny though. The guys did make a good point this last year. I should get like a little PO box so people can send me stuff when they want to, but I don't sit around and ask for things, because mostly we just run the group and do Linux and stuff, right? But sometimes people like to send me stuff, so I'm like, all right, this will be my risky package open of the day or whatever, right? All right, so the header, source, destination. There's other things that appear in here that are important. The version. There's only 2 versions of IP addressing that should show up here. It should be 1 bit right here. So look, this is the version is 1, 2, 3, 4. So it's 0 through 7. So that means this is the 4's position. So it should be right here. So it's 4, IPv4. Or it should be here and here on for IPv6 because that's the 4 and the 2, right? So if I just said something that was true, we could verify it. Watch this. I'm looking at the IP header. We come back here. I know this is going to be bright, guys, but this tool is bright. I don't think this tool has a dark mode. Let's see if it does. Does this have dark mode? I'm pretty sure this doesn't have dark mode. But if it does, then I apologize, guys. I've been, like, blowing you guys up this whole time. Could I be in dark mode? Oh, anyways. You don't want to share your legal name. Oh, I don't. Yeah, fair enough. Fair enough. You could, well, you could do it as a business too, I think. But yeah, I think that's right. Yeah, I don't know. I don't see it in there. Anyways, let's go real quick. IP, and we're version 4, which is 0100. That was the first one I said, because that's a 0 in the, oh, so it's actually, yeah, up to 15. But that's the force column right there. Boom. Force column, 1, good. Can I find an IPv6 address? Do we have an IPv6 one? So there's an ARP right here, and this ARP yeah, since it's ARP, it's not going to have it. Here's an IPv6 header, and in the Internet Protocol version 6, it's 110. So that's a 4 and a 2, so that's a 6 right there. You see that? Those are the only 2 things that should be there: IPv4 or IPv6. Now, hold on. So somebody's going to probably ask, could I write my own custom one and run it internally in my system? Yeah. Within the Linux world, yeah, you could write your own IP protocol. You could take what's out there, you could compile it, you can run it inside and recompile your kernels to use your version, and then you could capture that and you could have a different, or could you send, you might say, could I write an IP protocol packet that had like all ones in there just for funsies? Yeah, you could. There's tools out there that'll generate it. You can write it yourself inside of all kinds of different programming languages. You can go modify these and hand these things all over the place if you want. I think there's a launch command to do dark mode. There probably is, yeah. You know what? And by the way, like I'm much more aware of this when I deal with streaming, because people be like, my eyes. But I don't care with college students. You know why I don't care with college students? Because they're not people. No, I'm kidding. I'm kidding. I was saying that in game. I was saying that as a character in game, right? Now, I joke around about how my college students are not yet people. But the point is, here's an IPv6 address, and then I can go see about the source. There's the source address and the destination address, and this is multicast. So we were doing something with multicast at that time, right? So there we go. You read a bunch of RFCs and see if anybody else wrote. Yeah, RFCs are a great way to put yourself to sleep, too. I tell you guys, in the engineering world, if you're like, oh man, Scott, I can't sleep at night, I'm like, all right, well, try putting your phone down like an hour before you go to bed, do some reading. That might put you to sleep. And if that doesn't work, start reading RFCs, because RFCs will put you to sleep, man. They're definitely. Anyway, so, but my point is, we can know things or read things about these, and then we can go look at them in the tool and actually see that, yes, this is truly the format of this packet, right? All right, so then we get down here, and here's an IPv6 one, and it's the same thing. There's a version at the front, which we know is 0110, which represents the number 6. Boom. So IPv4 to IPv6, the major updates are geolocation and security. There's other things with modularity that's also built in there. But for the most part, there's a lot of, in IPv6, there are things that have been added where we can give more. Actually, I think I stripped it off of here. But here's the RFC. So if I don't remember, I can go read the RFC right now. right? So I'm always telling you guys, the RFC is right here. I can say, okay, hold on. RFCs will put you to sleep though. But I can come in here and I can see here's my terminology. Here's that. That's exactly the picture I have. Traffic class, flow control, payload length. What's in there? 16-bit unsigned integer. Length of the IPv6 payload. So this is the IPv6 payload can be differing sizes. All IP packets can be different sizes, and they tell you about how long they're going to be in the payload length field right here. Right? They calculate as this gets put on, it calculates the full size of everything. Right? Come down here, and then I might say, okay, IPv6 header, then our TCP data. So IPv header can have other headers that keep getting attached underneath, especially if we're fragmenting it, right? There we go, and then we come down. Encapsulation header, encapsulation security payload header, and then we can go down and read the notes about these. So guys, we have all this stuff that we can go to. What happens if you don't enable IPv6? Well, then you would never see IPv6 headers. You would only see IPv4. If you don't go IPv6, so let me show you guys in like a Linux system. Most systems, the way most things have worked for this to kind of be an easy transition. And by the way, I was in college for my undergrad from like 2004 to 2006 when I first got out of the Army. And in 2006, they were saying IPv6 will be the only thing in the next 2 years. And it's like, okay, buddy, now we're up in 2025 and we're still using IPv4 everywhere. But real quick, IP-BR ADDR, it'll show it to us in a brief way. Any of these, my loopback and my Ethernet 0, are doing what we call like a dual honed interface, or some people might call it like a dual layer stack, or IPv4, IPv6 stack, whatever you want to call it. But my Ethernet 0 is accepting IPv4 and doing traffic on IPv4, as well as IPv6. So this is kind of the way that it's been bridged and sliding over, where my device can do IPv4 or IPv6 stuff here until we're ready to go all IPv6 only. But I just don't, man, I don't see that. Yeah, Marion, all new things in the future are 5 years. Yeah. And then people will want things to stay. But no, Mindustry, if you had a lab, if you had a system at home and you said, I don't really trust IPv6, I'll just do IPv4 everywhere, you wouldn't hurt a damn thing if you turned all your IPv6 off. In fact, sometimes for troubleshooting, especially building newer systems, and we're trying to just eliminate anything that might be causing problems, and we're looking at logs and we're starting to see IPv6 addresses, or we think that things are communicating on other paths, we'll turn all of IPv6 off sometimes. So you can actually turn off what is that command? Yeah, sysctl-a grep-i IPv6. Here's all our IPv6 stuff. And we can actually turn it off at the kernel level if we want. If I turn it off at the kernel, it's not going to be working anywhere else. Right? It doesn't matter what other things you turn on or try to. Yeah, you could disable it. Yeah. A lot of people, because it's one of these things, and you guys hear me say this a lot. Like, as an engineer, I want to control things. I want it, like, and you say, really, that firm of a grasp? You're really that much of a jerk? Yeah, because you know why? My name is on a system. If I build 1,000 systems and I tell you they're going to work, but they all start breaking, people are sitting there cursing my name. And I'm like, I don't want people cursing my name. I want people saying, oh, hey, everything Scott builds works. So I control things. So like as said, IPv6, just turn it off. If I'm not using it, if I'm not communicating in any systems, there's no reason to have it on. That is actually the same exact concept of all security, right? If you're not using the window, close the window. How'd the person get in the house? They climbed in the open window. I'm not saying you wanted them in your house. I'm just saying you didn't not want them in your house. That's actually an argument people use, right? Like, I'm not saying it's your fault you got robbed. I'm just saying, like, you should lock doors you're not using. That's like the first rule of security, right? Like, cover all exits, cover all entry points. All right, anyways, so then down here at network layer, we've got the old way that firewalls used to work. So this is a little bit of history. Firewalls used to be what were called packet internetwork exchangers. So PICs, which is the PIX firewall that Cisco used to call it, actually comes from that term, packet internetwork exchange. That's an old way. If you use it, it's on you, but my specification states it's not used. Yeah. At the end of the day, firewalls represent, at a minimum, a connection between different autonomous systems. That's that term AS I use. Autonomous systems is a network engineering term, right? So if the firewall's here and my private network's in here, the way this communication has to occur is typically this firewall either has to have a stateful packet inspection or it has to not do things. Yeah, OSPF. Yeah, I had there was a cert called the CSPFA, Cisco Secure PIX Firewall Administrator, back in like the early 2000s. Yeah, that's old school. I used to run a couple of 525s for the school district I was at. They could do 180,000 concurrent connections each, and I ran them in a active passive failover between the two. And I used to maintain those firewalls. That was one of my jobs. So this is important to know if you're doing this, and this is something that you can inherently. So when I first started working at the school district, we had stateful packet inspection on. There's a trusted and an untrusted type of thing. Yeah, and then now they're all ASAs, right? Adaptive Security Algorithm or whatever they call them. But ASA is there. Oh, it's something security appliance, isn't it? Adaptive Security Appliance. But I think originally they called it the Adaptive Security Algorithm, even on the PIX firewall. That's what they called it. And then I think now they just call the device ASA. Anyways, stateful keeps track of stuff. Stateful is like a bouncer, and when you go to leave the club, they put a little wristband on, and then when you go to come back in, they let you back in. But if somebody doesn't remember that you were in, now you got to get rechecked out, wanded by security or whatever. Make sure you don't have any knives on you or whatever. So with IPv6, sorry, not IPv6, with a stateful packet inspection, if I want to talk out and then that traffic comes back, the firewall has remembered that traffic. Now, you say, how does it remember? Well, as I generate a web request, when I get to the TCP section, I want to talk to port 80 over here. And port 80 is the destination port. The source port is some bullshit number, 5563, 5563. That's just a number that my system selected to allow the traffic back. When the traffic comes back from that, the destination is going to be 5564, whatever I used, and the source is going to be port 80 from this machine, right? And the stateful packet inspection firewall is going to keep that log on there, right? What happened here? IPv6 rubbed me wrong when some money guy presented it and didn't want to say broadcast. He multicast. Yeah. Stateless. Every packet is evaluated both ways. So with stateless is typically how our access control lists work. Our access control lists are not aware of the traffic going out. And if traffic tries to come back in, they're like, whoa, we don't do that here. I don't know you as having gone out. And this will cause communication problems if you don't allow these things back in. So I actually have an example of a stateless one here in a second. But routers' access control lists tend to function and filter on these things. Network layer protocols, IP or ICMP. The transport layer protocol is reported down as the transport layer segment comes down in and gets the header on it. So TCP or UDP and even like real-time transport protocol and these other ones can be added as well. There's source IP and in extended access lists, we can use all this. In our old basic access control list, you could only use source IP, right? Then the destination IP and then the TCP or UDP port number. So all those port numbers can be blocked as well, all right? This is back to that access control list thing, and I call it the coin sorter problem. I don't think, do I have the coin sorter in here? No. All right, I'll just explain the coin sorter problem to you then. But what happens is you always test access control lists from top to bottom. So we apply this one. Are you denied? No. Come to the next one. Are you denied? No. Yes. Are you permitted? No. Keep going. Right? So if you're getting all no's and you get to the bottom and you're not permitted, by the way, this is a any, so it's going to permit you. But we tried to deny. We allowed some traffic. We denied other traffic. Then we allowed anything. Otherwise, at the end, there's always a deny any. That has to be there. Otherwise, there was no reason to do all this in the first place. Now, the reason I call this the coin sorter problem is this. Has anybody here ever seen a coin sorter? You like pour the coins in and then it tells you where your pennies and your nickels and your dimes and all that stuff are? Well, I want to ask you guys, does anybody here know what the largest coin in the U.S. currency is? I get different answers every time for this, but it's either a silver dollar or it might be like a 50-cent piece. They're both pretty big though, right? Like one of those Susan B. Anthony. What do they have? They have like the dollar one, and then they have a 50-cent piece. They're both pretty big. Sorry, largest size. We're talking about coin sorting. So, just real quick, does anybody know what the smallest is? The smallest in the U.S. is a dime. In fact, the dime in the U.S. is basically the same as a Canadian penny in size, right? In fact, Canadian pennies sometimes get... Yeah, so let's just say the 50-cent piece is the biggest, right? The reason I call this the coin sorter problem is this. What if I dumped all my money in there, and I'm the guy who wrote... I built my own coin sorter. And I sort and I check for 50-cent pieces first. So 50-cent piece is this big, right? This big around. And the dime comes in and it falls through the hole. Did I just count it as a 50-cent piece? Yes. Okay. Next one comes through as a nickel. It's a little bigger. Falls through. But I count it as a 50-cent piece. When I get all done, I'm going to think I have like $14 billion. But dollar coins are 1 point. Yeah, so let's say dollar coins are the biggest, right? Huge coins. You would never search for those first. So a coin sorter has to sort the smallest to biggest. Now, the reason I say that is logically we're going to do a thing. And what I'm going to tell you is what if the first thing I did in all these access control lists is I permitted any right here at the top. And then the next thing was, well, I want to deny this traffic. It doesn't matter. He was already permitted. When you hit an access control list and come down, the first rule that's active against you is the rule that goes. You don't continue going down. So the reason I go with the coin sorter problem, the reason I call this the coin sorter problem, is if you were to sort coins and use the biggest coin first, you would just always you get the wrong answer all the time. So you got to sort from smallest to largest. Well, your traffic is similar. You don't have to sort from shortest to largest. You just have to understand that it's in order. And once you bypass a rule or you allow somebody to go through, there's no other way to check them. So if you put your implicit deny at the top, that interface might as well be off because no traffic's going. If you put your implicit allow at the top, you might as well just take the access control list away because nothing else is ever going to get checked. Does that make sense? Hopefully that makes sense. I'm the only guy that calls it. It says it right here. Only Scott calls it that. No other engineer calls this the coin sorter problem that I know of. That's just that's how I call this. That's how I think of this. And access control lists, you're going to make them in routers and routers. And then you're going to make them inside of like AWS as well. So if you go for any of those certs, you do that stuff as well. Yeah. So firewall sieve. This is what it looks like in there. And this shows that stateless nature real quick because we're allowing ICMP in. So you can ping my devices. You can come in on port 80. You can come in on port 443. So you can SSH in. And then there's this custom rule. Look at this custom rule. If you come in from 1024 to 65.535 from this other network, from this other source network, I'm going to allow you in. So you say, well, what does that mean? That means if any of my devices in here, this is my inbound rule, if any of my devices in here had sent traffic out and were allowed on a different rule, and then when their traffic comes back from like a web server or a SQL server or anything like that, and they had used an arbitrary port, this custom TCP rule would allow that traffic to come back in from that network. That's what this does. If you didn't have this here and you went out, you had a rule to allow you out on port 80 and you talked to somebody in the 10.0.0.16 address and then that traffic came back, the firewall would go, whoa, 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 or this is network access control list at this point, NACLs. It would go, whoa, I don't know you, and it wouldn't let it back in. So this is a catch-all to allow things back in. Yeah. Yeah, hopefully this stuff's useful to you guys. You're always welcome to hang out, and thanks for coming by, OSPF. That's actually a great name. Open shortest path first for you guys that don't know. That's a type of routed protocol. Sorry, it's a routing protocol, and OSPF uses it's a link state routing protocol as opposed to a distance vector, and then it uses these areas or zones. They're called areas. Yeah, and then you can have shorter areas so that your link state algorithm isn't taking all the memory in your device. Yeah. Well, when you start talking networking, I'm like, I can almost guarantee he'd used OSPF, which is open shortest path first. So that's funny. Yeah, but I'm a Linux guy now. I've been a Linux guy for the last 20 years, but I started my career as a network engineer. And, I was in the Army, and I was an infantry guy, and I just went and decided to go and get my Cisco. Because it was Cisco stuff, or it was like I could have done like this HVAC stuff. And I'm like, HVAC stuff, I'm going to be working in the summer in Phoenix when I get out of the Army. I'm like, yeah, I'll learn the Cisco stuff and go sit in data centers. So that's what I did. Also, when I was in the Army, the average salary of somebody with a Cisco degree made $60K a year, which was not a Cisco degree, but with a CCNA, it was $60K a year, which was a lot in the early 2000s. A lot of money. I was like, oh man, I can't wait to make like 4 times what I make in the Army. The Army didn't pay me very much, but okay. All right. Anyways, then layer 3. We looked at layer 3 most of this time. Packages do the same as humans. Yeah. Open shortest path first. Fair. Layer 2 concepts. So we've got switching. The physical addressing is a big part of it. Address resolution protocol, or ARP, is how our system knows the mapping of local hardware addresses to IP addresses. Then there's also reverse address resolution protocol. The problem with redundancy in a non-hierarchical address space. The idea that, so if I just have a single path across all my switches are great, man. They're like, hey, you're not over here. I'm just going to basically bridge you out over here, because switches are just multi-port bridges at the end of the day. I don't see your MAC on this side. I'll send you out this side. And when there's one path, that's awesome. But when you're using hardware addresses and you're using multiple redundant paths, a problem presents itself, which is if my name is Scott and I'm in room A, but then I move to room F over here, and there's multiple paths to get to me, and somebody says, well, I know how to get to Scott. I saw Scott just a few minutes ago. I'll take this over to room C, and then from room C, he goes to room D, and then back to, and people start looking for me, but I'm over in room F right now, and then they get back to room A, and they're like, oh, I'm back in room A with Scott. Shoot, how do I send this over to Scott? And you don't know how to do it, because my name has nothing to do with my location. So when we talk about MAC addresses and hardware addresses, your MAC addresses, your layer 2 switches have no way natively to deal with the problem of redundancy. And you say, well, hold on a second. Can't I just put a bunch of switches, like you said, in parallel and not make them redundant? And I go, yeah. Do you want to run networks that have single points of failure? No. SPOFs, SPOFs are like the worst thing ever. So you say, okay, well, now I'll put 2 switches, but then now your switches get into these frame loops. And they can't pass traffic correctly. And sometimes the traffic does get there, and sometimes it doesn't, and it's a nefarious thing. So spanning tree protocol, STP, not to be mistaken with the Stone Temple Pilots, spanning tree protocol was generated to figure out a way to take this non-hierarchical thing and cause it to flow all the traffic one direction. So we're going to get into that here in a second. Let me, I've been talking for literally 3.5 hours straight. So let's stay right here real quick. I'm going to take a quick, get my camera off here. Let me take a quick break, put my little hourglass up. I do have to get to yelling at my students here in a little bit, but I'm going to go right here. And I'm going to say quick break. And then continue. And let's say go 8 minutes, because I like to walk around a little bit. And while we're sitting here on this, I'll also put Ranger Cam back up. What is Ranger doing in all the world? Shoot. Where is Ranger? Shoot. There's my top 500 stuff. Let's get rid of that, because I don't have enough space to see my my stuff anymore. Give me a second here, guys. Where is? Let's get rid of that. I've opened too many windows to see it at the bottom of my screen easily. Let's get out of there. One more second. Hold on. I'll find it. That's the syllabus stuff. Ansible lockdown. We don't need that right now. That's gonna take my whole break for me to find Ranger Cam. There we go. Also the DNS haiku from earlier. That's funny. All right, where's Ranger? Oh, look at that dog. All right, I'm restarting my timer. All right, it's 8 minutes. Go smoke him if you got him. There you go. Hang out. I'll be back. All right. I'm back, but still on break. I do got to get off here in the next few minutes for talking to my college students if they show up. I do my huddle sessions on the weekends for all my students. Yeah, huddle sessions for my students so they can come and study and work on stuff. They don't always take advantage of it, but I at least sit in there for them. In case they do show up. Look at that Ranger dog. Man, that dog he is out. He does not care. Ranger is out. Yeah, look at him. He's mostly relaxing right here. You're like, you just pointed at all of him. Yeah, that's him. There's Ranger just passed out. And he's laying on a smaller bed too, because like this bed's bigger and then this bed's on top of it. But I've seen him laying on this and putting his nose over here because he likes different textures. He likes to put his nose on stuff. That's my dog for you. And he's not a little dog either, man. Like I try to emphasize with you guys, like he doesn't look very big, but he's not little. If I go back over here to like our pets, that's him when he was laying on the other one. Hold on. He's not a little dog. That bed is not very big though. That's him being Ranger. Same picture. No. Where's he at? Hold on. That's him kind of laying on that. That's his little llama. He's had that llama since he was as small as it, and he doesn't chew stuff. That's Phoebe. That's Ranger laying down over there. Yeah, thanks for coming by, Marion. We're just we're hanging out. We're not working too hard. I'm mainly here. The main reason I stream is to let you guys know that we got a Discord. You can go hang out with engineers, talk shop. Doesn't cost anything. You just hang out down there. Hang out in Discord. See what kind of goodies are going on down there. So, yep. All right, let me turn myself back on here. Oh, yawn really hard. Like Ranger wants to. That dog. We'll blame DNS one more time before we start back up. And then we'll come back over here to this. I'll move this out of the way. I'll still give you guys a few more seconds for your break. You guys can have until the end of the time, just in case anybody walked away. But yeah, switching your physical address doesn't change just because you move around in the network. Yeah, YouTube. We got to 3,500 on Discord. We're trying to get. My next real goal is like over 10,000, but I mean, we'll take any small little, anytime we hit any smaller number. Like we'll say something when we hit 5,000. Fisherman also put it in the bot, so when people join, it always welcomes people. But when they hit certain thresholds, like I think when we hit 3,000, it said welcome to somebody. Like it specifically said you're our 3,000th or 3,500th, I forget now, person. So the goal is like just, keep growing it. Hopefully people find stuff that's useful to them, find ways to get into the industry, because that's what I want to do is get more of you guys doing this stuff so that I can go retire, make the next generation do it, and then I can get out of the Linux space. No, I'm just kidding. I'll always play in this space. I'll always be here doing this stuff, but. VLANs, so I'll give it a minute before I start again. Fly over, yeah, YouTube. We actually, so it's actually funny. People in UK, we got a lot of guys from UK, and they wanted to hop on and have like a UK meetup, and I was like, oh shoot, if they're gonna have a UK meetup, we need to have like an Arizona or like a US meetup first. So I know like the guys were talking about it in New York, having like a New York version, because we have a lot of people in New York, a lot of people in California. Robodom's really the only one who's like officially done like a meetup, because they were doing the Scale Expo, and like a couple other guys, they all got together and then they met up at the Scale Expo. So we actually have photos, I think from 2 years ago now, isn't it, Robodom? Where we sponsored some of the junior guys to go because like there were tickets for Expo. Robodom just is smart. He volunteers, and then he just gets to volunteer, and then he can go sit in on the different stuff. So that's kind of cool. Yeah, it was like a little impromptu meetup. So we've technically had one in the U.S. already, but yeah, we need to get the little groups in the different areas to meet up. All right, so let's go over this real quick. We had gotten down to here, and then VLANs are 802.1q tagging, and there's some other proprietary protocols that are there, like ISL with Cisco. ISL is only if you're in an all Cisco environment, though, for that to be able to work. VLANs do break up broadcast domains within the same switching device, so that's good. And once you implement VLANs, the only way to make your VLANs talk to each other is through a router. That's just the way that it works, because the 802.1q tagging that gets put into the frame affects it. So I don't know if I have anything in my monitoring now. So let's go look real quick. Oh, that's the wrong one. That's a different device. Don't worry about that one. Over here, not there either. Hold on, I'm losing it because I have more than one screen open. If the Ethernet 2 frame has tagging in it, it'll be added right in here. So you'll see it for if there's a different VLAN. Now I actually am running VLANs in my home lab, so I technically should be able to. I should be able to see that if we were to do like a TCP dump on. If I went to here, and I'm on Rocky 1, and then over here I'm on Rocky 1. So if I did here, and I just set like a ping to 192.168.11.1, right? So we got a ping running. And over here I did like a TCP dump dash I ETH0, right? Yep, ETH0. So TCP dump dash I ETH0, and then dash W, we just throw it to like temp, and then hostname dot date plus percent capital F, and then say dot pcap, so capture dot pcap, right? So we'll just capture this. Oh, I don't even have TCP dump on here. DNF, what provides TCP dump? It's because this is a very minimal server that I built. So it's just TCP dump, so we'll install it. All right. Yeah, Mindustry, you can ask whatever you want. Yeah. I will answer, I think, whatever I can. And if not, I will always just reference you guys back to the dudes down in Discord who are pretty good. So this is capturing stuff, and it doesn't look like it's doing much, but I know over here we're at least pinging over there, right? And the ping is happening on an internal interface that's operating on 192.168.200, getting tagged and then going over there and then coming back. So we should see actually interesting. I'm not 100% sure if we will see it. All right, so that's all done. We'll stop this here. We got 261 packets, right? ls-l on TCP, and here is that Rocky capture. We're going to exit out of here. We're going to SCP Rocky 1 temp Rocky 1. There we go. Down to here, right? And then we're going to chmod 644 on TCP dump Rocky 1 dot TCP dump, move Rocky 1 to temp, and then we'll, let's see, can we do it from there? No, we'll go to this one, SCP it down. So we're moving it in my home lab down to where I can grab it out of my personal machines, and then I can open it. So we're gonna SCP from werewolf temp Rocky 1 to temp. That's fine. Yep. And then we gotta put an asterisk on this because we want to grab anything Rocky 1 down. Do I know this password? It's annoying. All right, long way around to get to here, where then I do CMD on this box, right? So on my home machine, CD to downloads where I want to put it, pscp.exe, which is a tool that you can download when you download PuTTY. It's just pscp. You can also use, you have SCP right on here, so you can do that too. We're going to go schampine at 192.168.11.245. Temp Rocky 1 dot 2025, anything to here, and then my password is download it. Good. Now, if we want to see everything that was happening in that system right then, we'll go to File, Open. Let me see my... I think that went to not responding quickly. That's funny. Because it should find it right here. Users, het, downloads. There's my PCAP. So this is all the traffic that was just happening when we were pinging and doing all that stuff, right? Here's all my stuff going on. And what I should be able to see is if I come in here, do we see, I'm actually interested if in the frame we see, and we might not see it because it's been stripped off by the time it gets back here. Yeah. It's stripped off, but this device is in VLAN 1, and it's actually getting stripped off. So technically, I'd probably have to watch it on the other. Anyways, the point in showing you guys that is you can go look at the VLAN's 802.1q tags when they're there. In my case, they've probably been stripped off because the devices are doing it, and that's not a big deal. That's fine. All right. So let's go down here. Here's what the header of a frame looks like. And the frame is the first one with a frame check sequence at the end. So there's a preamble, which says, hey, we're starting off. And then there's a destination and a source address and then a field type. These are 6 bytes each, which is 48 bits long. And that's that hardware address that we've been looking at. And then if we've got a type of Ethernet frame, that's where it's going to put it. All right. Switch management, but this is what I was talking about earlier. Switches are great if you just had one line across them. But if you have them going multiple paths, there can be, like, the idea. So to get from here to here, you guys looking at the screen go, well, I could go, boom, easy. But your switch, when it comes in here, your switch doesn't have a hierarchy. It doesn't know something should go out this way or this way. And it's just looking at the frames, and it's basically like, oh, it's got to get to Scott. Well, I know how to get to Scott. I'll go to switch D. And switch D is like, well, I've seen traffic from Scott on switch B, so it goes to switch B. Switch B is like, well, I've seen traffic from Scott over here on switch A, and it just starts going like this forever. So switching, because of the limitation of the address type and the fact that it's non-hierarchical, can't flow data towards a place like IP can. IP is naturally hierarchical, so data always flows towards your default gateways and flows out of your network, and then it gets updated and goes the way that it's supposed to go. And if devices don't know what to do with it, they send it to their next hop and their gateway of last resort, and that's fine. Switches don't have that. So how does a switch get all the traffic to go to the right place, right? And the way I always explain this to you guys is, for me, if any of you ever, has anybody here ever done dishes? Anybody here ever done dishes? Like, I was in the Army, right? So I've definitely done dishes. But I was also, I had 4 brothers, so we had pretty, bigger meals when we were kids because there was a lot of us, and we'd have to do all the dishes after, right? So, like, I've done dishes. But has anybody here ever, like work? I mean, if you work in a place where you have to do dishes, you got a big sink, and you're taking that water, and typically you're washing it all off in some, cleaning water, and then you've got a rinse place, right? Well, if you've ever went to rinse off a plate, this is how I always think of this in my head. So this is how I'm going to explain it to you guys. You can put, like, you could take a plate like this that's flat, and you could start to fill it with water, and the water tension will cause it to start to rise on that plate. Most plates also have a little bit of a concave to them, right? So you can kind of start to fill them up. Well, you can actually hold, it's actually surprising, you can hold a lot of water on a plate because of water tension before it finally, like when you pick away for the water to fall, it'll all slide off to that side. Have any of you ever done that? Like, you washing? Yeah, I grew up dishwashing, right? And I did it in the Army. So well, as an infantry guy, I did it. So you pick the way you want it to eventually fall is my point. The same thing is going to happen with spanning tree protocol. These devices don't have any hierarchy to them. So we're going to say one of you becomes the root, and all data are set to flow that way. So what they're going to do is one becomes the root. One of them, they do an election process to become root, and one of them will be the root server, or the root switch, and all of the other switches will flow their data to them by turning off redundant links. If any link goes down, they will automatically recalculate and make sure that they can get to the root bridge, or the root switch as it is. They call it the root bridge because switches are all just multi-port bridges. That's all they are. And then they would recalculate and they would send it over. So it looks kind of like this. Spanning tree protocol works by switches passing around a BPDU. It's called the Bridge Protocol Data Unit. They storm when they first come up. They don't know anything. They don't know what's going on. And then again, they're going to elect a root bridge and calculate how to get there. And it's almost like that plate with water. You're going to make it all flow off to the one side, right? So here's the process. They elect a root bridge. You can also administratively set it by setting which one you want to be the root bridge in the there's these general randomly generated numbers, and you can set it to be the lowest, and then it'll automatically be the root bridge. Then they elect their root ports, they elect their designated ports, and they figure out how to send traffic that way. Without getting too much into it, because again, this is just a primer. Like I've done satellite dish work too, delayed, but no, in this case, I'm talking about literally like washing dishes, like washing dishes and filling them with water and then pouring them out, because that's how this kind of works. There's no hierarchy here. This is a bad design until you implement STP, spanning tree type protocol. So the things you need to know is bridge protocol data units, what your update timers look like, and this kind of stuff. This is what it looks like. You've got a blocking, a listening, a learning, and a forwarding, and then we could disable them by shutting them down. This is an eternity to systems, though. This can take, spanning tree can take like 90 seconds to completely what we call converge. It's actually funny. I made it 3 hours and 55 minutes before I used the word converge. You guys know what I can't believe it took me that long. Converging is one of the most important concepts of all the things I've been talking about. Converging is when all the devices on the network, according to their protocol, see things the way they should. Convergence is super important. Like convergence is when the storm stops, when a network first comes up and MAC address tables are being repopulated and spanning tree protocols are being set and that kind of stuff. A convergence of 90 seconds on a network is an eternity. That is so long. That is like if you show me a meme from 3 weeks ago on the internet, I'm like, seen it. What generation are you from? Freaking boomer, right? No, but what I'm saying is like it's so long ago. So Rapid Spanning Tree Protocol can go through all this, RSTP, which is a newer version, in like 5 seconds, which is much, much, much better. 90 seconds, guys. 90 seconds, you've lost customers. Your website, that's 90 seconds is a long time to go through a convergence process, right? So Spanning Tree looks like this, right? We elect the root bridge. All the data are going to flow to the left now. And now we elect root ports, and that's how we're going to flow data, and we start to block. So somebody coming from over here, switch F isn't going to go this way anymore. It's going to come down here. It's not going to send traffic up this way anymore. It's going to come over here, and then it's going to go out the root port towards the root switch and go out. Now, you'll say, are those open? They are technically open, but they're sitting in a blocking state. So then if somebody comes in and cuts this fiber here or pulls this, they would immediately start blasting bridge protocol data units everywhere and go, what the hell's going on? They just start flipping out like the robots in C-3PO, just like flipping out, right? Like I'm going nuts. And then they would recalculate and the traffic would start to go this way to get to the root bridge, right? And then, you cut this one as well. And now it doesn't, we don't need to recalculate. We're good. But the systems would actually still do the process of sending out BPDUs because they want to talk. So Spanning Tree Protocol is defined by IEEE 802.1d. So if you wanted to go read more about it, there's an RFC on it, and you can see the implementation. But it prevents loops by calculating paths to avoid potential loops and artificially blocking links that are up. These are true links that are active, but they are blocked for now, so traffic can go that. No, it's a layer 2 protocol. Spanning Tree Protocol takes a layer 2 device, because these layer 2 devices have no hierarchy to their MAC addresses. So Spanning Tree Protocol is a layer 2 protocol for sure. Oh, that's my little thing that says I have to get off of here. Okay. Then we got Rapid Spanning Tree Protocols, Trill, and SPB. I don't know anything about Trill or SPB. I just know they exist. Rapid Spanning Tree Protocol can go a lot faster. All right, guys, I do got to get off of here soon. Switch port, there's a bunch of other topics like when you do stuff with a switch, you got to do a no shut command to make sure that it's up. If you're not using a port, you should use the shutdown command to turn it off. So turn off ports that aren't being used. We call those dark ports. That's a common term. Hey, I've got 48 dark ports on that access mode switch. So yeah, we can add that new lab or whatever you want to build. You can use switch port security to limit MAC addresses to only the MAC addresses that are seen on there, and it keeps people from plugging in like wireless access points, what we call rogue access points. You want to limit those in your system. Switch ports can be trunked or in access mode. Trunked means that any number of VLANs that you allowed to be trunked can be trunked across them, and then they're the same on both switches. It's interesting to note, if you have two switches sitting there and there's no trunk between them, and you have VLAN 123 over here and VLAN 123 over here, they are not the same VLANs between those two switches. Once you draw a trunk between them, and there's a trunk there, and the trunk is trunking those access, it's trunking those VLANs, then those are the same VLANs. But otherwise, they are not the same VLANs as far as the network goes. All right, link aggregation groups. You can take like 3 or 4, typically we'll do like 4 ports between switches that are all 10 gig ports, and we link aggregate them to be 4 ports acting as one lag. And that one lag is now a single port operating at 40 gigs. So we can get a lot more speed through there. If one link goes down, it's bad, but we're still at 30 gig speed between 2 devices. So these drawings here where we had this, these could be multiple ports, but they're link aggregated groups. So now we have really high speed between them, but the lag can still be turned off by spanning tree protocol. So that's important to know. And then, Wireshark again, and then I have a whole bunch of other stuff to do. But anyways, I gotta get off here. I don't have time to go through all of these things. We go down into all the way down to layer 1, and then we do some additional topics. This is on there. There's a YouTube for this, and it's also available in Discord if you guys need any of those links or anything like that. So, guys, I got to drop off because I got to go yell at my college students. Right? I'm only mostly kidding about that. But we will talk later. Let me on the Twitch side. Let's go raid somebody. See if anybody we know is on. Maybe my favorite to raid is. Oh, he's not on. My favorite to raid is not on, so let's go raid. We'll go raid into. Oh shoot, who are we gonna raid? We'll go raid into Alt F4. So our raid message is do all the Linux, and I will see some of you guys. Probably I might be on later when you guys are doing. Oh, there's a group starting up too. So if you're in our Discord, there's a group starting in about 15 minutes. You guys can go hang out with them as well. All right, I'll talk to you guys later. Take care.